Hi, I'm Tony Alicea, and this is the first 6 hours of my course, Understanding React. In this course, designed for both beginners and experienced devs in React, we dive under the hood of React to understand how it really works, diving into even its source code to build an accurate mental model from the ground up that will help us to use and debug React properly. Interestingly, this video will end where most React tutorials and courses begin, as we'll endeavor to understand everything we need to know to understand fully how even a basic React application works, including topics like JSX, reconciliation, and the fiber tree, hooks, and much, much more. For the full course, you can go to understandingreact.com or follow the link in the description of the video. I hope to see you there. But in the meantime, enjoy the video. Hi, I'm Tony Alicea, and welcome to Understanding React. In this course, we'll dive under the hood of the incredibly popular JavaScript library, React. We'll gain an understanding of how React really works, and that will enable you to both code and debug more confidently, more quickly, and more enjoyably. There are a lot of React jobs out there, so whether you're using React for your own personal reasons or to use it for employment, I hope to help you to gain a deep understanding, the kind of understanding that will serve you well through your entire development career. And in this course, we'll follow a core principle. Don't imitate, understand. This course won't be about simply walking through some kind of project where you're following along with me coding, and we pretend like that's somehow going to teach you everything you need to know in order to build different applications. The truth is, we're always faced with new challenges in development work. So by just imitating, parroting someone else, we never really learn to deeply understand what we're doing in a way that will help us when new situations arise. Instead, this course will be about helping you truly understand, and while we will code and we will build a project, the project work will come later. We're going to focus piece by piece on deeply understanding what React is, how it does what it does, and how you can then best use it to build websites and web applications. I'm so excited to be on this journey with you. So let's begin understanding React. Let's talk about what you'll need to be ready for the rest of this course. In this course, we'll use Visual Studio Code as our code editor. If you don't have Visual Studio Code, you can get it by going to code.visualstudio.com. For later portions of the course, you'll also need Node.js and the Node Package Manager, or NPM. This allows you to run JavaScript directly on your computer and use a variety of utilities that are used for preparing React code for real-world use. You can find this at nodejs.org if you don't have it already installed. For much of the course, as an alternative, you could also use StackBlitz at stackblitz.com and do all of the coding inside your browser. I won't be showing you how to do this in this course, but you can create a new React project or a new blank JavaScript project, and the coding interface is essentially the same as what you find inside Visual Studio Code. Once you have Visual Studio Code installed, you can go to Extensions, and you'll need a server, something to make your computer act as if it was the internet. I use the Live Server extension, so you can search for that and install it. Once you have it installed, there will be a Go Live button in the bottom right of your Visual Studio Code. And once you have that, you're going to want to go ahead and create a folder and then open that folder with File, Open Folder, and from there you'll be able to create the files that we'll use for this course. And that's it. Once you have Visual Studio Code, the Live Server extension, and Node.js installed, you're ready for the rest of this course. You're ready for Understanding React. The initial portion of this course will be focused on a singular goal. We'll try to understand how React really works. And along the way, we'll understand what the problems are that it's trying to solve and how it helps us solve them. In order to help us focus on our goal, we're going to take a deep dive into React itself, and we'll structure that deep dive around understanding a basic React app. An app like this. It's incredibly simple. I have 2 counters, and whenever I click on a button inside each counter, it updates the number of times I've clicked. This is the kind of simple example app you might see in a beginner tutorial. But we're not going to just try to understand how to build this app. We're going to make the effort to completely, fully, deeply understand everything happening inside React in order for this app to function. And that is a very different goal than you'll find in other courses. By deeply, fully understanding how React works, you'll be able to use it better, and perhaps even more importantly, debug it better. You'll be able to quickly understand when there are problems and make good choices about how to structure your apps and use React's various features. So from this point forward, we're going to back up and eventually make our way to an app that's just this, the 2 counters. But you'll be very surprised at just how much we can uncover about how React really works by focusing on this simple example. And from there, we'll be able to branch out into the more complex. Even if you've already been using React, can you really explain what's happening under the hood fully? If you're a beginner, this is a great place to start. And if you're not, I'm asking you to trust me. Come along for the ride and see just how much more deeply we can understand React. When we say deeply understand what's happening under the hood of React, what we're really talking about is the React source code, and that is available to you. React, although built by Facebook, is open source, meaning that you can read its source code and even try to contribute to it. Its source code can be found on github.com/Facebook/React. And throughout this course, we'll take a look inside the source code to get a sense of how React is doing what it's doing. Now, there are 2 important points to go along with this. 1, code always changes. And my goal is not to update this course every time React code changes, because it changes every week. And that's okay. It should. So our goal is not to understand every line of React code, but to get a sense, an overall picture of how it's accomplishing what it's accomplishing, and even to enable you to take a look inside the React source codes as it changes and understand it. The other point is how I want you to come to see the React source code and React itself, rather than thinking of React as some kind of utility, rather than thinking of yourself as becoming a React developer, which is a term we'll see even in job postings out there. I want you to simply think of React as other people's JavaScript code, because that's exactly what it is. And that means it's just other code that you can understand and that you're using to make your development life easier, or to accomplish particular projects, or to get a job. But it's not some secret black box that can't be understood. So let's start that right now. React is just other people's JavaScript code. And as we begin to understand it and write our own JavaScript code on top of it, we won't let it intimidate us. You can understand React. Let's move on. In this section, we'll talk about the document object model and what's called declarative programming. We'll begin to break down the kind of work that React is doing for us and how that underpins understanding what it's really doing under the hood. To begin our journey into React, let's talk first about the fundamental data structure that underlies everything we experience on the web. This is HTML and trees. In this course, I assume you're already familiar with HTML, but let's think about HTML from a computer scientist's perspective. Not only is HTML human readable, that is, if it's authored well, but it maps to one of the fundamental data structures commonly used for storing information in a computer with the intent of later traversing, that is, moving around and through that data structure in order to find information, make changes, updates, edits, additions, etc. That data structure is a tree. And that generally means we have a node or a portion of the tree, a particular point in the tree, which is connected to other points in the tree. If you've seen tree data structures drawn before, represented visually, you might have seen something that looks more like this. For the purposes of this course, we're going to represent tree data structures like this, which is equally valid. It'll give us a bit of wiggle room in order to add later pieces of the puzzle when it comes to how React really works. It also maps to how React has chosen historically to implement trees and helps our mental model when thinking about how trees will be processed. If you're not very familiar with tree data structures, well, realize that what we really mean is an upside-down tree. We tend to draw the root at the top and then move our way down the tree, that is, across the branches from there. And we use phrases borrowed from family trees, such as the parent and the children. Understanding the work that React is doing for us is about understanding how it uses and manipulates trees. So let's keep this in mind and move on. Now that we've talked about trees, let's get more specific about one of the two types of trees we're dealing with when building an application using the React JavaScript library. It's the type of tree really that we use in general when doing front-end web development. This is HTML, the browser, and the DOM. As we've said, we might write HTML to mark up our document, giving that meaning to the computer. Each of those HTML elements ends up forming parts of a tree, a root, parents, children, grandchildren, etc. And when our browser reads in this text file, it creates objects in the computer's memory that represent these HTML elements. These individual objects then have references to each other, such as their children. That is, one object knows where another object is located in memory. We represent that visually with some arrows, but the basic idea is to form, in a way, a tree of objects. And that tree models or represents the HTML document that was written. And so we refer to this tree as the document object model, or the DOM. Big word alert. Whenever you see a big word alert in this course, that means we're about to explain a phrase or a word that sounds a lot more complicated than it really is. That's very common in technical discussions. And we want to be sure that we're speaking the same language, that we're on the same page. So we'll stop, describe the term, and then move on, knowing that the term isn't nearly as complex as it sounds. So, big word alert. The document object model, or the DOM. The DOM is a collection of objects in the computer's memory that represent the HTML elements that define a web page. It provides the ability to analyze and change the document being presented to the user. So as you change the DOM, what the user sees or reads also changes. Once you pass HTML to a browser, what you're actually dealing with is the DOM. The HTML is read and is essentially discarded. The DOM, the collection of objects in memory that form a kind of tree, is what we're dealing with. And therefore, it's ultimately what React's JavaScript code is dealing with. So to have a proper mental model, HTML, which is really just a text file, is read in, and the browser converts it into the DOM, a collection of objects in the computer's memory. The browser then takes that information, those objects in memory, and does what we'll call render. And part of that rendering will say paints the web page to the user's screen. In this case, we have a list of 3 items, and so that's what we see in the browser. We'll stop here and say that this term render is an important one. When we're talking about DOM trees, then when we render the DOM tree, we're talking about essentially making it visible, making it available in the browser to the user. Later, as we talk more about React, we'll also see the word render used in terms of React itself, and that will actually be a different definition. And this sometimes causes confusion. Since we'll be dealing with two different trees, which we'll see in the future, just remember when we talk about rendering, and we're talking specifically about the DOM tree, the one that the browser creates, we're talking about actually drawing the web page, making it available to the user. Let's move on. Now that we've talked about the DOM, let's talk about changing the DOM in code. This is DOM manipulation. As we said, we start off with text, the HTML, which is converted by the browser into the DOM. And then that is used to create what we see on the screen. An additional and important piece of the puzzle of how we got to where we are in modern web development is the idea that the DOM can be manipulated. That is, we can change the contents of the DOM tree after the HTML is read and the DOM is created. When we change the DOM tree, the browser re-renders. It updates what the user is interacting with to match the new DOM. And this is the foundation of how many modern websites and web applications work. How is it possible to manipulate the DOM? The browser provides an API. Big word alert. An application programming interface, or API. That is, the functions, objects, URLs, etc., that define how a program can be communicated with. An API is how we allow our program to be talked to by other programs. Inside the browser is a lot of code. The code that defines the DOM is part of that code. The browser APIs are methods with which we, in our code, can talk to the browser's code. For example, we might append a child, adding a new element to the DOM tree. The append child function is not a standard JavaScript function. Instead, it's provided by the browser, which lets us call it in our JavaScript code. And after we call it, it causes the browser to re-render. So as we think about the browser, we're really thinking about two pieces of the puzzle. Within the browser, we have the JavaScript engine. Most modern JavaScript engines are written in C++ that runs our code. We also have the rendering engine, often again written in C++, that does things like paint the DOM tree to the screen. Both of these engines sit inside the browser. And so we can write JavaScript code that can give instructions to the rendering engine. This happens via these browser APIs. For example, let's write our first bit of code. I'm going to have this basic HTML document, and I'm going to reference my JavaScript code. I'll put it inside the body because we're going to reference the DOM elements. If I put this script up in the head, then the DOM elements wouldn't have been created yet when the JavaScript runs. By putting it in the body, I'm assuring that the DOM elements are already created before the JavaScript is run. Now, let's suppose I add a bit of HTML. I'll create an unordered list, and inside it, I'll put 2 items. Now, inside my JavaScript code, I'm going to go ahead and start using the browser APIs. The document object is part of the browser APIs. It's not part of the JavaScript engine naturally. It's provided by the browser. There are various functions inside the document object, like being able to get a reference to one of those DOM elements in the tree. I'll get it by its ID, which was list. I can also create new DOM elements that aren't currently in the tree. Let's create a new list item. Then I'll set the text of that list item. Again, these are browser APIs. .text content is provided by the browser. And then I'll use append child. It will add my new DOM element to the existing DOM element as a child. So the UL will get a new LI. When I run this, hitting go live, I get 3 items. Remember that what was actually downloaded was 2 items. That was the HTML that was written. But the DOM, and I can view the DOM by inspecting it as if it was HTML, but this isn't the HTML that was given. This is the current DOM elements. I can see that third item. We could make it a little bit easier to see it be created by doing it on a timeout. The set timeout function is another browser API. It's not part of the JavaScript standard, but it's provided by the browser. I'll make this instead a function, and I'll run this 1 second later. So what will happen is this HTML will be read in as text by the browser, converted into DOM elements, and my JavaScript code will be run. But this code to add that element will be run 1 second after the rest of this JavaScript is finished. If I refresh, we saw that third item being added. When append child was run, the DOM was updated by the browser, and the act of manipulating the DOM caused the browser to then re-render the web page. So the act of building dynamic web applications is often the act of manipulating the DOM. That's basic and has been around for a long time. The question that modern front-end JavaScript libraries and frameworks are often asking is, how do we manipulate that DOM? There is a cost to these things. Browser has to do work both in updating the DOM and updating the screen. Plus, it's a question of how difficult we make this to do in the code. How much work do I, the developer, have to do to manipulate the DOM? That fundamental question of saving work, both the browser's work and our work as developers, is at the root of what React is designed to do. It's time for a conceptual aside. Conceptual asides in this course are lectures that are side points, but they're important to understand in order to be able to move forward and understand the main points in a particular section of the course. In this conceptual aside, we talk about imperative versus declarative programming. And really, this time, we're just going to do 2 big word alerts. Imperative programming. Imperative programming is a style of programming in which you describe how a program should accomplish a task. For example, to illustrate, if I was instructing a robot on how to tie its shoes, in imperative programming, I might first tell it to bend over, lean down, then take its fingers and hold each shoelace in each hand, step by step by step. That would be imperative programming. But then there's another form of programming, another style, called declarative programming. Big word alert. Declarative programming is a style of programming in which you describe, that is, you declare, what you want the program to accomplish without describing how. This would be, for example, as if the robot had a command called tie a shoe, and all you did was tell it the left shoe or the right shoe, and maybe what kind of knot to use. But you may not describe every step in the describing how. Now, that said, declarative programming is essentially taking a step away, an abstraction above the imperative programming. That doesn't mean that there isn't imperative programming going on somewhere. A declarative system is always built on top of an imperative one. Something has to give the explicit step-by-step instructions. So don't think that declarative is quote-unquote better. What it is other people's work that you are coding on top of. It makes our life easier as developers because we're relying on other people's work. And that's generally true in programming in general. We rely on the programmers who built the browsers. We rely on the programmers who built the JavaScript engines. And if you're sitting inside a declarative programming style, then you're relying on the people that wrote the imperative code under the hood. Now, let's take a look at imperative versus declarative programming from a DOM manipulation and JavaScript point of view. And that will lead us into understanding what some of React's fundamental goals are and how accomplishing those goals have contributed to React becoming so popular. Let's try coding something simple using both declarative and imperative programming. Let's start by explicitly telling the browser what to do. This is the DOM and imperative programming. Remember the app that we're going to fully understand in React, where we're just increasing a count as we click a button? Let's try to do something like that. I'll update my HTML. I'll use an article element, which really means this is a standalone section of my HTML document. I'll give it a header. I'll give it an H2, as I imagine perhaps I'd have an H1 later on. Then I'll have a sequence of text, so it's appropriate to use a P. I'll say you clicked. Then I'm going to emphasize how many times the user clicked. I'll start with 1, and then say times. Finally, I'll have a button that will run a function when clicked. And I'll say click me in the button. We'll get rid of much of our previous code, and we'll go ahead and grab that EM element that holds the text of how many times the button has been clicked. And we'll create our setCount function. So we know we're going to need to get the current count. What I'll do is I'll take the value, the text value inside the element and convert that to a number. Then I'll add 1. Then I'll set the text content of that element equal to the new value. And we'll run it. Now I start clicking and the value updates. So this works just fine. The important point is that this is imperative programming. Notice that the function setCount called when I click, I tell the browser via the JavaScript engine every single step of how to update the interface. I have to go get the current value, increment a value, and set the value seen visually. Updating that value is updating the DOM, and that causes the browser to re-render. So as the DOM is adjusted, the browser chooses to update what the user sees. I've given the browser instructions via my JavaScript code, explicit step-by-step instructions. This is imperative programming. And as you can imagine, as apps get larger and more complex, this becomes complex and difficult to manage. And it's a lot of extra work for me, the programmer. Ideally, we would take this imperative programming, move it off to the side as a series of functions, and then we could think more in terms of declarative programming. Let's see that next. Let's think now about what a declarative version of what we just did might look like. This is the DOM and declarative programming. Remember we said that declarative programming means we're just saying what we want and not instructing the computer exactly how to do it. But that declarative programming is always built on top of some imperative programming. So, for example, let's create an object. I'll call it the count app, and it will have 2 functions. It will get the count, and it will set the count. In my get count, I'll simply return the current value stored in the DOM. So get the number, and then in my set count, I'll set it equal to whatever the updated value is. Now I can change my set count function called by the click to get the count. I'll do some logic, make sure it never goes beyond 5, for example. If it does, I'll set it back to 0. Otherwise, I'll increment it by 1. When I run this, it works, and when I go beyond 5, it goes back to 0. So in this code, I have an imperative piece of code where I'm saying exactly how to update the DOM, the step-by-step instructions. And I have a piece of what would be a more declarative piece of code. Note that I'm not saying anywhere how to update the interface. I'm just saying that the values that the interface depends on have changed. I'm able to write some logic, but I don't have to get into the details of how to update the DOM. If this entire object was in a separate file and was referencing it, I might be able to then write my app without ever having to talk about how to update the DOM. It would be a more declarative approach to updating the interface. The plumbing, the work of updating the DOM has been abstracted away from me, and I can just focus on the logic of the app and the values that the app depends on. This basic idea defines what React is. It's a library to help you write more declarative style web applications and websites. It lets you focus on the values that the interface depends on, and not so much about how and when to update the interface itself manually. In an extremely simplistic way, this part, the imperative count app, is React. And this part, this function, is the code you're writing using React. It's an equivalent concept, although obviously far more simplistic. Does this make sense to you? Again, that's why I say it's important to think of React simply as other people's JavaScript code. And we could say more specifically, it's other people's imperative JavaScript code. That's why it's important to think about React as simply other people's JavaScript code, and more specifically, other people's imperative JavaScript code that will let you write web applications in a declarative way. That makes the developer's life, our lives, easier. It lets us focus on what the app is supposed to do and less on how the app is going to update the DOM. Now that we have this basic concept in mind, we'll move on to start to understand what that imperative code is inside of React and how it's doing it. In this section, we'll start to truly dive under the hood of React by looking at a fundamental JavaScript structure that it uses to do what it does. We already said there are two trees that we're dealing with React, the DOM tree, which we've looked at, and now we'll start to look at the other tree, a tree of what's called React elements. It's time for a conceptual aside. In this aside, we talk about recursion. Big word alert. Recursion. Recursion is when a function calls itself, meaning I write a function, and within the body of the function, I call that same function that's being run. For example, I might have a function A, and in the body of function A, it calls function A. This is possible because by the time the function is actually executed, it exists. So it can reference itself, essentially. But each invocation of the function, each call, gets its own space in memory. So function A is running and calls function A. So that invocation is now the currently running function. And that calls function A, etc. The problem here, of course, is that eventually the computer will error because this will never stop running, and eventually the computer will run out of memory space for all these functions. That's why, in practice, we always have some logic to finally finish the function, where a function returns. So we might have A, which calls A, which calls A, but something is usually changing, variables being passed to the function, for example, and once they reach a particular value or some other logic, the function returns. So the function completes its execution, and then we go back down the stack of functions to where we have all of them complete. Let's try doing it ourselves. I'll get rid of the markup and code that we wrote in the previous lectures. And I'll create a simple function. I'll pass it a number to this countdown function, and I'll output to the console the number that I passed. Then I'll recurse. I'll call the same function again, passing to this new invocation whatever number I gave it, -1. So for example, if I said 5, I would output to the console 5 and then call the function passing 4, 5 minus 1, which would output to the console 4, then call countdown passing 3, 4 minus 1, etc., etc. Of course, this would eventually error out, so I'll need to have some logic to say at some point the function finishes. I'll say in this case, once our countdown hits 0, I'll just return, and that will make sure that eventually all the functions finish. I'll then get the recursion started by calling the function initially with the value of 5. Now I'll run this, and there's my recursion. The first invocation printed 5, then called the function again with a 4, 3, 2, 1, 0, the logic hit, and the function returned. That means that the function that called it finished, etc., 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 back down the stack of functions. This is recursion at its most basic. The reason we're talking about this is that recursion is a very common way in coding to traverse a tree data structure. Big word alert. Traverse. To move across or through something. In the case of a tree data structure, we mean to move from element to element. That is, from parent to child to sibling, etc. I move around the tree using recursion. So within React, because React is dealing with trees, there is this idea of traversing the tree. Now, when we talk about traversal and recursion, recursion can get expensive from a computer memory and processing standpoint. So React actually avoids recursion as much as it can, but still the fundamental idea is recursing through a tree. We'll see in the next lecture how recursion helps us do that as we begin building our mental model of how React works under the hood. We need one more conceptual aside before we actually start using React. Here, we're going to talk about POJOs, plain old JavaScript objects. Big word alert. A plain old JavaScript object, or POJO. That's simple collections of name-value pairs. That is to say, the objects that you're accustomed to creating in JavaScript. An object has various properties, which have a name and a value. A very simple and straightforward collections of pairs of names and values form a basic JavaScript object. I'm going to delete the JavaScript code from the previous lecture. And let's think about how we might form a JavaScript object or set of JavaScript objects that describe the HTML that you're writing. If I was to do that myself from scratch, what might that look like? Well, let's suppose I'm going to make a simple, plain old JavaScript object. I'll call it Markup. And I'll try to describe what we created previously, where we had an article which had an H2 for a counter and then a paragraph showing how many times a counter had been clicked and a button. But instead of defining that with HTML, I'll try to describe it using an object. Now, this will be my own object, so the browser won't know what to do with it. But it's just me trying to find a way to structure an object so that I can describe what HTML might look like. For example, I might say, well, I need to know the type of HTML element. So I'll have a name-value pair of type with a value article. And then all elements may or may not have children. There would be more than one child potentially, so I'll represent that as an array. And then inside that array, I might have various other types. For example, inside the article, I might have an H2. And that H2 has children. In the case of HTML, the text itself is a child. So I'll call that maybe type text and value, well, the H2 had the text counter in it. And let me make sure I wrap this so that we see this is an object. Again, this is just me coming up with my own interpretation. This is nothing official. It's nothing the browser would understand. But you start to get the picture. I've created my own object that describes what the HTML should look like. I've already done some work to fill out the rest. So I have children of article in H2 and its sibling, which sits at the same level as the H2 of P. Paragraph tag also has children. It has text, which is counter and then a space. Next to that, a strong element, which has itself children. An EM element, which it has children, the text, and the number of times something has been clicked. Then after that, another space and the word times. So this would say counter 1 times. And then there's a button, which also has text as a child. Again, this is just me coming up with a way to describe what I want the HTML to look like, what I would want the DOM to look like without actually updating the DOM. Since I kind of have my own version of the DOM here, you might call this a virtual DOM. That is to say, a DOM that isn't really the DOM. It's a fake DOM, a fake tree of fake elements. If I was to log this to the console, there I see my object, article, which has 3 children, H2P and button. The P, for example, has 3 children, text, strong, and text. Now, of course, nothing has happened on the screen because this isn't actually the DOM. It's my virtual DOM, my fake DOM, my custom DOM. And for anything to happen with this custom DOM, I would have to write some imperative code. That is to say, you could think about this object as declarative code. I'm saying what I would like the DOM to look like, but I'm not saying how to update the DOM to match my object. So now I'll need some imperative code to make my declarative code work. Over in my HTML, I only have a main element, which is the ID app. Going to go ahead and get it. And I want to stop there and think about something. If I log to the console this DOM element, there's a lot in there. It's very large. There's a lot of functionality. There are a lot of methods and properties on this DOM object. So this real DOM object is much heavier, much bigger than the simple object that I created. It's a lightweight DOM in many ways. But again, it doesn't actually do anything. So it's a useless DOM until I write some imperative code, the step-by-step instructions of what to do. Remember from last lecture, anytime we have something structured in a tree data structure format, we can use recursion to loop through it. Well, this is essentially a tree. Because of the arrays, I have children that are siblings, and then each can have its own children, so grandchildren, etc., in a tree format. I'm going to go ahead and write a function that's intended to be called recursively. It's called add elements. I'm going to give it one of my plain old elements, and I'm going to give it the real parent DOM, where those elements should be attached to in the real DOM. Then I'm going to figure out what kind of real DOM node I want to make from my fake one. So, for example, I'll just base it off the type. Now, this is very simple. I haven't dealt with all the possibilities, but just for this conceptual aside, we'll be able to get an idea. If it's a text node, then in the DOM, I would create a text node, which is its own kind of node. And I pass to it the value of the text node, which I'll use my value property in my object. If it's not a text type in my virtual DOM, then I'll just use create element, which creates a standard DOM element. And as a note, I chose to match the types like EM and strong to real DOM element types. So I can just use that type when creating an element. Then I'll check if there are children in my fake plain old JavaScript object. If there are, I'm going to loop through all the children, that is across all the children that are siblings of each other. I'll use a for each, which will let me loop through each item in the array. I'll call each item child, and then I'll recurse. The child is now my POJO element, and the new DOM node that was created is now the new parent. Let's think about that for a second. If I start with the main as my real DOM node and article as the element, because that's the top level of my virtual DOM, my fake DOM, then it's going to see that that's an element and create a new article element. That is a new DOM article element. Then my POJO has children, the H2 and the P. So it will start with the H2 when looping and call add elements for that H2 in my virtual DOM to attach as a child of the new real article DOM node. I'll log to the console to help see what's going on. And then I'll do the actual work of making it appear on screen by updating the real DOM. I'll take the parent DOM node and append a child, the new DOM node that I just created. Since we'll start with the main element that's actually really existing in the DOM as the parent, it'll begin appending the article. And then to article, it will append the H2 and the P, etc. Since my object isn't of infinite size, I don't have to worry about an infinite loop. Then I'll call it. I'll use my markup as my start, my markup object, and main as my starter DOM node. And there it is. It doesn't work. I haven't attached any code to the button. But if I look at what's outputted to the console, I can see the recursion happening. For example, we keep going back to article because we keep attaching more child elements to the article that are siblings of each other. And within those child elements, like strong, we can see that we had an EM before that and a P before that. As we dug down into my virtual DOM, it created all of these real DOM elements. And so my declarative code now works imperatively. Because this code already works, I could just go up into my virtual DOM and create a new sibling. For example, I could say there's another sibling next to the H2, maybe an H3, with some text inside that says, this works. And it does. My imperative code recurses through my tree to create the real DOM. So I can then just declaratively change my fake DOM, my virtual DOM, and let the code that I wrote update the real DOM. And as you can imagine, this is easier than doing all of these create elements and create text nodes myself if I'm thinking through the logic of something. And then I could be much more intelligent about how I update the DOM. Because remember, updating the DOM is expensive. Do I really need to recreate the entire DOM every time? Could I look at the DOM as it exists and say, well, all you did was add an H3, so let's just do that. And in fact, that's exactly what React is doing, which we'll see later. For now, keep this in mind conceptually. I've created my own object structure that acts as a sort of virtual or fake DOM. And then I have my own imperative code that loops through my fake DOM to create the real DOM or to update the real DOM. This should be your mental model of React. So what does React's fake DOM or virtual DOM look like? That's next. In this lecture, we start diving in and actually using React. This is creating React elements, and we'll look at the plain old JavaScript objects that React makes. For the portion of the course in which we're diving into React source code and understanding how it works, we're going to use the most simplistic way to add React to our web application. Now, I want to say immediately, this is not how you likely should do it for your projects. You can do it this way if you're only doing a very simple piece of functionality on an existing web page, and maybe you only need to do it once. But later in the course, we'll talk about how you likely should set up your React web applications. But for the purposes of learning, this will be an excellent way to set them up, the simple way that will let us really see how the source code is working. The React documentation site actually helps us with this simple way. It tells us that we need a root element, that is where all of the real DOM elements will be added. We already have that with our main element. And then it gives us 2 script tags to use to add React to our site. And those should be before our own script. And we'll stop here on this page. We won't do any of the other things that the React documentation site says to do because we're focused on fully, truly, deeply understanding what React is doing. We'll drop in the 2 script tags. Now, why do we need 2? Well, we'll get more into that later, but at its most basic, we have a React JavaScript file, a bunch of other people's JavaScript code, and we have a React-DOM JavaScript file, again, more of other people's JavaScript code. This React file you can think of as containing the fake DOM, the fake elements that React has set up for us to create. And you can think of React DOM as containing the imperative code that looks at the fake simple JavaScript objects created by React and actually does the updates in the DOM. That is all those append child and create elements, etc. that we did for ourselves in the previous lecture. Let's get rid of then this extra code that I've written, and we'll use React's code instead. React said we need a root node. That is, React needs to know where is it going to start adding the real DOM elements within our existing page. I'm going to start adding all of our real elements to this main element. But I could have various different elements on this page and only have React actually insert elements into elsewhere in the tree. For example, I could have had some article and then have a section, and I could have had this be the root node and have other things going on the page that React never touches. But for the purposes of understanding, I'm going to go ahead and simply keep it to a primary root node. That's the only thing on the page. Now, the fact that I added those script tags means I have some objects available to me already, other people's objects written by the folks that write React. Let's output to the console the object called React. And here it is. There's a lot there, a lot of functionality that is available to me because other people wrote all this code. I find things that look like I might know what they do, like create element is a function. I see a lot of things that you may have heard of if you've been using or been researching React. Let's start with the word use. All of this is available to me because I loaded those scripts, because I loaded React. So let's use a few of these features. I'm going to create a React root. By the way, there's also a React DOM object that also has a bunch of features. I'm saying to React, this DOM element, that's where you should start adding all of the elements that we'll create via React itself. That's the root. Then I'll ask it to actually render. And in React's case, when we say render, we mean take the declarative way of creating elements, plain old objects, and then create the real DOM elements from that. What do we give to render? Well, I'm going to make a function. Writing React applications is all about writing functions. I'll just call mine app, and it's going to return something special. React.createElement, and inside create element, it takes a few things. It takes what kind of element I'm creating, some options, and any children. Now we'll stop here for a moment. Create element is actually not how you should create React elements anymore. It used to be a way to create elements, and so it's still supported in React so that older React applications don't break. We'll show you in a bit how you should create React elements in your applications. However, React.createElement is so simple and straightforward. It's a terrific way to build a mental model of what React is doing. And again, it still is supported inside React. Just note, this is not what you should be doing in your applications. We're just doing this right now so that we gain a good mental model and understand. And we'll look at the right way very soon. For now, understand that the goal is simply to create plain old JavaScript objects, what React is calling React elements. JavaScript objects that React has defined to represent real DOM elements, or collections of real DOM elements. Now that I have a function that gives me a React element, I can give that to React to render. Now, this may look a bit odd, but I'm not creating an element from what's returned from the app function. I'm turning the function into an element. Notice I didn't call the function. I just gave it the function object. So I'm saying turn this function into a custom React element, into one of those plain old objects. And then React will call the function. Since we wouldn't see that happen, I'm calling the function myself again. Let's prove that React is calling the function. I'll log to the console called app. If React is calling the function, I should see this twice. I'm calling it myself, and React should be calling it. Well, first of all, it worked. The imperative code inside React added a real DOM element. If I inspect this, I see that it's sitting inside my root, what I defined as my root. So the child was added to that real DOM element. If I look in the console, I see my log of React itself, the React object. Then I see React calling my function. And I see my own call happening. And here I outputted what was returned from the function. Notice I'm outputting the return. I'm calling the function. So it's returning what this is. What did React.createElement create? It created an object that has something called props, which contains, in this case, children. It has a type, button. But notice it doesn't have too much. Compared to a real DOM element, it's quite lightweight and much simpler. React was doing exactly what we did in the previous lecture. It created a simple collection of objects, a simple tree structure, then looked at that tree structure and figured out how to create the real DOM elements. And when it did that, we got the real ones on the screen because once the DOM was updated, the browser chose to re-render the page. So just one more time. We said where the root is, that is where React should begin adding real DOM elements. And we said, here's the function to call. We'll treat the function as its own basic object. And in JavaScript, functions are objects. React will then know what function to call. It can look at the element that it creates and figure out what to do. For example, if I log to the console what that actually creates, we can see that again, it created one of these simple React elements, the simple type of object, But the type, instead of being something like button, is actually a function. So it knows that this particular little node in its own tree is a function. So it knows then that it would need to call the function to get what it's returning. And if it's not a function, then it knows it could just look at the type and decide what kind of DOM element it should create. So now we're getting a picture. A tree of React elements is a tree of simple objects which define types. And a type could be a function, or a type could be essentially a string, which will represent real DOM elements or represent a function that needs to be called so that we can get even more React elements out of it. I give React my function, and React calls it. And when I say I give React, really I'm just utilizing other people's JavaScript code, and they decided to create an object called React and React DOM to put all of this functionality on. When I asked it to render, it created its own virtual DOM and then updated the real DOM to match. And that update we then see when the browser re-renders. Make sense so far? So let's keep this mental model clear in mind. We've started creating what's called React elements and letting React update the DOM itself. In other words, I wrote something declarative and React made it work imperatively. So now we've seen React elements, but really we're dealing not just with React elements, but React element trees, a data structure of plain old JavaScript objects. We've already seen that when we're dealing with React applications, we're actually dealing with two trees. We're dealing with the real DOM tree, complex objects used by the browser in order to render to the screen the website or web application. And it can also be used to render in other circumstances, such as for screen readers and other ways of getting the information from the website or web app. That's the DOM tree. Now we've seen that we also have another tree, the React element tree. These are simple objects used by React's code that represent the DOM tree, but they don't actually do anything without React's imperative code. We can think then of the React element tree as a fake tree. It's not real, it's virtual, and it's much more simplistic. It gives us an idea of what the real tree should look like. And the DOM tree is the real tree. It's more complex, and it's the thing that users actually interact with. Keeping these two trees in mind is key to understanding what React is doing. Let's work on creating a bigger tree. I'll get rid of this console log and this one here as well. And we'll look at what we're returning from our app function. Remember, we said that the create element method that React provides lets me say the type, which could be a DOM element, or it could be a function, which React would then call, and then children. The children could just be text. So React's imperative code would create DOM text elements, text nodes, or it could be other React elements. In fact, I can keep adding more and more children, as many as I want, on the end of this function. Now, if I did that, this would get really hard to read. I'd like to do it in multiple lines. So we'll do a little JavaScript trick and put this entire set inside parentheses so that I can just split this into multiple lines of code, and the entire set of lines will be treated as a single return statement. That's just a syntactic trick. And I'll try to recreate what we created before. I'll have an article, which will then have children, and I'll just indent the code to make it clearer where the children are. I'll create an H2, which itself has text as a child, a second child of the article will be a paragraph tag. Paragraph tag itself will have a child of text, and a third child of the article a button, which itself also has some text. And then I'll finish this create element. This is all inside this parent create element call. And let's see what happens. There it is. If I look at the DOM, I can see inside my main, it added the article root, and then the H2, the P, and the button, which each have text as children. React's imperative code updated the real DOM to match my declarative tree of React elements. And what does that tree actually look like? I'll call my function again and log it to the console. There I see React itself, and then here's my tree. Notice what it really is a single React element, and that React element may then have children, which it does in this case, under this value called props. It's an array. Each array element is a React element, a simple JavaScript object defined by React. And so we see the H2 has also children, in this case just text, the word counter, and then a space, etc., etc. So this code, provided by React, which I then used, created a tree of simple JavaScript objects. And the structure is very similar to the one we created ourselves previously. I have a type, and I have an array of possible children. React used that tree to figure out what the DOM should look like, and then the browser re-rendered when the DOM was updated. Make sense? Next, we dig just a bit deeper into the timing of what React is doing. This is just a quick conceptual aside about the DOM itself and those DOM elements. This is DOM element references. When I'm using something like get element by ID, the browser is letting me search the DOM and get a reference. So for example, if I log this root node, I can see that what I actually have is this DOM element. The console in this case has chosen to output it as HTML, but what it really is the DOM object, or more specifically, the variable is pointing to the location in the computer's memory where that object lives. If it didn't exist, I couldn't get a reference. So if this main was gone, the reference would be null. And of course, in this case, React wouldn't know what to do because it would say the target is not a DOM element. The DOM element doesn't exist. When I asked the browser to search for it, it wasn't found. There was no reference because I asked to find it by ID and it couldn't find an element of that ID. I'll put it back and there's my reference back again. The point here is that we need a DOM element to already exist in order to be able to get a reference to it when we're searching through the DOM. This small point will help us to figure out the timing of when React is doing its DOM updates. Let's look more closely then at what's happening and the timing of getting from the React elements to the real DOM elements, from POJOs to the browser. We've already talked a lot about imperative versus declarative programming, about saying what you want to happen versus how it actually happens. And this can help define how we think about the two different trees we're dealing with in React. You can think of the virtual DOM versus the real DOM as a tree of React elements, which represent what we want the DOM to look like, versus a tree of DOM elements, which is what the user is experiencing right now. For example, in this case, I want 3 LIs, and the user is experiencing 2. The imperative programming then needs to update the DOM to look like what the React element tree looks like. And that's an aspect of what React calls rendering. Remember how we said that the word render is used multiple times in these cases? Well, the DOM renders the DOM elements to the screen, making a visual web page. But React renders a React tree or a React element tree. That is, it creates or renders this tree of React elements. We'll take a deeper dive into what the process looks like to update the DOM elements to look like the React ones. But here, let's ask a question about timing. Let's try to get a reference to the DOM elements created by React. I'll search the DOM tree using a method called getElementsByTagName, find all the article elements, and I'll show you a second thing that we could do, which was try to actually get the first item in that list. Let's see what we get. I'll log both all the elements that are articles that I can find and the first one. And it's empty. Now here's a tricky thing when it comes to the console. When I try to open and inspect an object, it's going to look at its value currently. At the moment it was logged, we can see that it was empty. There's the empty brackets. But it might be confusing if you click it, because all of a sudden now we see the article, the one that was created by React. But that's because when I open this, when I click this in the console in the browser, then we got an updated version of that request to go find that article. But at that moment, it was empty. And we can see that because when I went to grab the first one, it was null. So these DOM elements didn't exist, even though I had already called render. Why? Because all of this happened before React does its work. React does its work asynchronously. That means it uses a browser feature to say, I'm only going to start running my imperative code once the JavaScript engine is available. That means it's going to run the rest of my JavaScript code first, then the browser will say, that's done, and the code in React has added some other JavaScript code to run once the engine is available to be used again. So when I ran this code, there were no DOM elements created by React yet. I can prove that by running the code after React does its work. Now I'll do it very simply in this case. I know it will run this code pretty quickly. So I'll run some code about a second after the rest of this code finishes. Now this is also running asynchronously. So what's going to happen is this code will all run. The render will tell the browser, I want to run some code when the JavaScript engine is available. This will finish. React will run that code, and then this timeout will also trigger. And the code I put here will run at the very end. And I'm just going to copy the exact same code. And there we go. In the first case, it's empty and null. And in the second case, it found the article, because by that point, React had done its work and updated the DOM using its imperative code. If you look really carefully even inside this main DOM element, when I refresh, you can see the DOM elements being added, but it really happens very fast. Did you see those 3 dots appear? Watch again. They weren't there, and then they were. These DOM elements were added after the fact. React does this so that the screen doesn't end up being frozen while it's doing all these DOM updates before any other JavaScript code that we've written runs. It's trying to make sure that its code doesn't block the user from interacting with the page, and block other code from running. So now we're building a mental model. I can create a tree of React elements, tell React where in the DOM I want to start adding those elements. React will wait for the rest of my JavaScript code to finish, and then look at my tree of React elements, which is how I want the DOM to look. Look at the actual tree, which started off as just empty, and make the updates so that the real DOM matches the React element tree. Make sense? Make sure this is clear to you, because it defines so much of the rest of understanding React. We've already seen the difference between declarative and imperative coding, and we understand that declarative coding always stands on the shoulders of imperative coding. In this section, we'll begin to dive under the hood of React and its imperative code that enables us to write in a declarative way. This is React DOM updates. and we'll take a look at React's imperative code that updates the DOM. To do that, we'll make a change. Instead of getting react.development.js and react-dom.development.js from an external source, I put these URLs in my browser, I downloaded these two files, and I put them here under a folder I called scripts. So I'm going to reference my own copy of these files, React's JavaScript code. Since it's in the same website, I don't need cross-origin. And that's it. Why? Because now we'll be able to dive into the actual JavaScript code that these files contain. And that will enable us to see how React is really working. To start with, I'll go to my app.js file and get rid of some of these extra calls, set timeouts, calling the app function myself. Instead, I'll just ask React to take my app function, which I give it, this function object. It's going to create a React element from that function object, then build the virtual DOM, its virtual DOM of React elements, and then update the real DOM to match. My app function is returning a single element, an article, which has children. And each of those children have text as a child. Now we'll go to react-dom.development.js. I'm using the .development versions because they contain comments, all of the white space, carriage returns, etc., that make the code easy to read. You shouldn't use this in a real production environment. For starters, it's much bigger than you actually would need in a real production environment. But it's perfect for learning. Now, here's a question. If we're trying to investigate a framework like React, look through its code and understand what it's doing, how do you think we should start? Well, for one thing, we know some of what React must be doing. It must be updating the DOM, using those features provided by the browser API. Some of that work we tried ourselves. So things like append child must be here inside React's code. It must be doing the actual step-by-step work. So if I want to find some key spots inside the React code, for example, about updating the DOM, I can look for browser API usage. I'm going to look for append child. And I'm going to look for a spot that looks like the basic usage of that browser API to add something to the DOM. Here it doesn't look quite right. There's an append initial child. That's interesting. And look here. I found a function called append child that takes a parent and a child and uses the DOM function, the browser API, to edit the DOM, append child, and then it passes that child object to it. There's also a commit text update for updating nodes that just contain text, the text value. And I see append child to container that inserts or appends nodes into a parent node. So this looks like it might be where React is doing some of that core imperative work of updating the DOM, the step-by-step pieces. So what I'm going to do is, well, I could step through this code in the browser, but what I'll do here is I'm going to add some logs to the console so we can see what's happening. I'll use string literal, and here I saw that React's call to this function passes the new text. Again, these aren't functions that I'm using in my code ever. This is all happening internally to React. This is code that React is calling within itself. But I'll add some logs so I can see what's happening. I might say here just appending child. And then down here, because child is probably a complex option, I'll add another separate console log of the actual child object. I'm curious what that looks like. It's most likely a DOM element, not a React element. Then down here, I'm going to go ahead and say that I'm either inserting a child in the container, and then I'll log this child that was passed to the function here, or I'll do something similar. I'll say appending child to the container. And I'm also curious what the parent node looks like. So I'm going to log the container is and then that parent, which is also likely a DOM node, because this is the actual DOM work via the browser APIs. And I think that's enough. Let's try running this. And here we are. I see the calls. I'm going to refresh because sometimes the console chooses to output HTML when it's a DOM element, and I actually want to see the individual pieces. So now I can expand this like a normal object. Sometimes after you open the console and you refresh, things will be outputted a bit differently, at least in the case of Google Chrome. Now, here's a question. Is this what you were expecting to see? I see a single append child to container. Here's the child that was appended, the article element, and the container it was appended to was my main element with the ID of app. That is, it appended article into this main element. And if I look at the DOM, there's article inside main. So article appended as a child of main. Maybe you were expecting a bunch of console.logs for each of the elements that would have been created inside this article, like H2, P, and button. But let's think about what's actually happening. Article already contains H2, P, and button. Remember, just article was returned from our app function. So from both a React element tree and a DOM tree standpoint, article is the only thing being attached to main. And then article itself already has its attached children. So it makes sense that the most efficient way to update the real DOM to look like our React element tree was to build up the article DOM piece of the tree with its children, and then just attach this branch, which already has children in it, to main, a single append child. Now, this gets even more interesting. If I open up the article element, this is the DOM element. Remember, it has all of these properties that come along for the ride as part of the browser API. But it has two properties that normally don't exist on a DOM element. Two properties that start with __ React. For example, if I look at this second one, it's an object, and inside the object it contains an array called children, which have three elements in them, each of them a React element, the H2, the P, the button, but they're not the DOM elements, they're the reference to the React element tree. So it looks like React is adding its own properties to the DOM elements before it attaches them to the real DOM. In fact, it's attaching references to the matching React element tree, which must be helping it do its work. That's interesting. And if we go down then, there is a standard browser API property called children, but that isn't an array. It's called an HTML collection. This is the browser DOM API way of collecting HTML elements, and that has the real DOM H2, the real P, the real button. But if I open one of those up, I see these properties that React added to the DOM element again. And this one has a child that's just the string, the text. So we're starting to get a picture. The real DOM has been updated to match the React element tree, but each of the DOM elements created imperatively are also created with some extra properties attached to the object by React. And if we go into the main, the parent container, it also has some React properties, like something called React listening, which is set to true. So now we're starting to get a mental picture. React has its imperative code updating the DOM. It's doing so in as an efficient way as it can, and it attaches other things to these DOM elements as part of its work. And we're going to look at some of these things like Fiber Node, for example, in detail as the course goes on. That said, I really want you to be thinking in terms of how can I learn a framework and come to understand and appreciate it when I first start using it, or even after I've used it for a while. If you were starting a new project with a partner and they had already written a bunch of JavaScript code, wouldn't you most likely at least take a look at their code before you started doing a bunch of code yourself? Yet funny enough, a lot of us use frameworks, which is just a bunch of other people's JavaScript code without ever looking at it ourselves. We're missing out on an opportunity, well, two opportunities. One, to understand how things really work and to reduce the intimidation factor of all this code. And secondly, we're missing out on a chance on what I call an open source education. These are a lot of very good coders that wrote this code, and it's been reviewed many times. So we can learn from how they write code as well. So I encourage you to take a look for yourself. Download the files. Now, they will likely be different from my files. They may not even be at the exact same line numbers, but that's okay. I'm not going to re-record all of this every time React changes because React changes daily. It just wouldn't be possible. But my goal isn't for you to memorize exactly where things are inside React source code. My goal is for you to feel comfortable in opening up the code of a framework like React and to start digging around. So go ahead, open the latest version of React, whatever that is for you right now, and do a search for Append Child. See if you can find where React's DOM code is actually being run. Start to get comfortable. This is what we'll be doing throughout the course, and the expectation will never be that the code that you see here in these videos will look exactly like the React code currently when you're looking. The goal will always be, let's think about how we can get a picture of what React is doing. And even if the code does change, React's core mental model is not changing. We're getting an understanding of how React is doing what it's doing, which will help us to use it better, debug it better, and to just be better coders overall. So, taking these ideas and taking this picture, the beginnings of a picture of React's imperative code, you're ready to continue taking a dive into understanding React. Let's move on. Ultimately, it's React's job to update the DOM, and it's our job to tell React what the DOM should look like. But to make that job of telling React what the DOM should look like easier, React breaks down those pieces of the React tree into what we call components. Big word alert. A component. In React, a function component is a function that returns a React element. And that element may contain other React elements as children, as we've seen. A function component is intended to be called by React. We hand the React code our function, knowing that React will, at some point, execute the function. And those functions, well, just like you can call a function multiple times, components by their nature are reusable, because that's exactly what they are. They're just functions. But you likely won't reuse every component in your React application, because in React, essentially, everything is a component. Everything is a piece of the React element tree that describes how you would like the DOM to behave. So, for example, suppose I have this simple React element tree. I have a section element, and inside that, a list element, ULs with their LIs. But I could redefine that UL and its LIs as a function that returns, and I'll just use some shorthand here, because writing React.createElement or something similar would take up a lot of space. But just the idea that we would return an unordered list element, which it itself would then have LIs, list item children. And again, these aren't DOM elements. These are the simple React elements. My list function would return a React element UL, and that would make it a function component, a list component. I would hand that to React, or it would be inside of a tree that I would hand to React, and React would ultimately call that function as it processed the React element tree. When React calls that function, the UL is returned. And so React knows that in the spot in the tree where the list function is, should instead, in reality, be what's returned from that function. The list component becomes what that function returns, the UL, which happens to have LIs inside of it. By creating an app function, I've already created a function component because it returns a single React element, article, which happens to have children created inside this React create element call. But let's take this and turn it into a component. I'll change the name of my function to counter. So now it's a counter function component. And I'll still make a base app. But that will return, let's say, a section will go inside of main. And I'll put an H1, no other parameters, and it will have text counters. And then a sibling, another section that will then contain the counter element. That will be a child of section. And instead of giving it a standard React element, I tell it, create an element from my function. And there you have it. This works because I put the React statement right next to the return. Notice in the other one, I wrapped it in parens because I wanted to put it on the second line. So this is just a syntactic difference, depending on how I wanted things to look. This may not seem too important now, but we'll see why in the next section it's something you need to remember. So I'm giving React my app function component. It's building the React element tree. Remember, we're not touching the DOM yet. We're building a section which has an H1 and another section in it, and inside that it has another element that React will look out and see that it's actually a function object. So it will call that function object eventually, and that function object just returns an article, which happens to have some children. App returns a section element, counter returns an article element, and that's it. But inside the section, there are children, and inside the article, there are children. Then React will do the work to update the DOM so that it matches the React element tree. And there it is, counters, and then the counter that came from the counter component. Notice we're still only appending the root, the section in this case, because inside main is now section. There's an H1 and another section, and inside that, we call the counter function component. That function component returned an article, and there it is, which had children inside of it. The DOM then has been updated to match the React element tree. And I've created a separate reusable component that outputs this article with the H2P and button. Make sense so far? In the next lecture, let's talk about how pulling this out into a component, extracting this into a component, as it's sometimes said, makes reusability extremely easy. It's time to continue talking about components in React, why React structures things this way, their advantages, and how React really calls components under the hood. This is components and reusability. And when we say reusability, we mean the DRY principle. Don't repeat yourself. Save time, effort, and unnecessary complexity by reusing pieces of functionality wherever you can. Here's a question. Let's suppose that I want a second counter. That's what we set up in the initial example when we started this course, remember? How would I add a second counter to my app? Well, if we think in terms of the DOM, we know that we've defined each counter to be an article element with the H2, P, and button children. So if I had a second counter, what would it look like? Well, if I edit this, I would essentially have two counters, two article elements. Now the question is, how would I achieve this in code? We've already said that React is going to call our function. Our function will be attached to the React element tree. The function object will be converted into a React element object. And then whenever React is looking at the React element tree and it sees a React element that is a function, it will call that function and attach the element returned from that function to the tree. I've attached my counter to a section element as a child. So if I want a second counter, what do? If you're thinking that I should add a second counter child, you're right. And React will treat this as a separate React element, a separate instance of the function object, and React will treat this as a separate React element. Although it's being defined by the same function, it will be two different function calls. Essentially call this function once then a second time. If you think about what this approach looks like inside the React element tree, if I have multiple components, multiple function components, for example here, a list component, what this really is a React element whose type is not an H1 or a P or an article, but its type is a function component. Its type is the function object. Because React then sees that the type of element is a function, React is going to call the function as it comes across it in the React element tree. Then attach that returned element to the element tree in the position where the function object was. If the function component was used again, it's really just another React element in the tree whose type is that function object. So the function will be called again. And what will the results look like of the React element tree? Just another replacement. The two function objects aren't influencing each other in any way. It's the same as if you just called a function twice and stored the results separately. So when we run this example, having added a second counter, we see both counters. And the DOM looks as expected. Two articles attached. And what would you expect our console logging of the append child calls to look like? Still, just one call, because both of those are inside the primary section that's actually being attached to the DOM in this case. We'll see later when this gets more complicated. This is actually a great opportunity as well to take a dive under the hood and make sure we understand what's actually happening at a JavaScript level inside React's JavaScript code. So here's a question, and this is true no matter what framework you're looking at and diving into. If you want to understand what it's really doing, how can we go about reverse engineering the framework? Well, in this case, I've given the React library a function, and I know React is going to call my function. My question is, where does it call it? I'm going to the Sources tab, and I'm going to step through some code. Now, if you're not familiar with stepping through JavaScript code inside the browser, that's beyond the scope of this course, but it's something you should definitely look into and be familiar with for debugging your applications. This is going to allow me to literally stop the program at a particular line, see what's going on, and move slowly through it. What I'm going to do is set a breakpoint, stop the program when the counter function is called, whenever this is running. To do that, I'm going to refresh this page. Program stops. And I'm going to look at the call stack. All of the functions that have been called so far to get me to this point in the program. So my counter's been called. And if I click, there's a function called render with hooks that's actually calling a variable called component. If I look up a little further, I'll see that this call render with hooks passes a component to this function. And in this case, we see that component is my function counter. So what we're seeing here is React is going through the tree. It comes across a React element that is a function. It calls it component here. And because it's a function, it runs it. See the parentheses? It's calling my counter function. And it's passing an object called props and another argument. We'll see more about that later. Then it takes whatever returns from the function, puts it in a variable called children, and moves along with that through the tree. It's going to do that in a recursive-like way, where it's going to go through all the children, and if any of those children are function components, it will call the function. We can see a bit more if we keep going down the call stack. The render with hooks function was called inside something called mount indeterminate component. And if I scroll a ways down, we realize that at some point, React identifies what I'm doing as being a function component at this point in the tree, talking about something it calls work in progress. We'll see more on that later as well. This was called from a function called begin work. So React is moving through the tree. There's something called work in progress. And it actually is looking at the type of thing in the React element tree, and it's a counter. Now, I'll tell you now, I'm simplifying things a bit. We'll get a little bit deeper into what this fiber node thing means and how what we're calling the React element tree actually gets more complicated. But for now, we can think of this as looking at the React element tree, seeing my function counter, and saying, now we're going to try to mount this component. And if you think about mounting, it's like mounting a picture on the wall, attaching the component to the existing tree. Then we see inside that function, eventually, React actually renders the component, meaning it's going to generate that piece of the tree. And in our case, we'll mark it as a function component. And when it sees that it's something that can be called, it's going to call it. It's going to run our function and pass it a variable, an object called props. And that's what's calling our function. But guess what? Not just once. If I click keep going, it calls it again. Why? Because we've added 2 counters to our React element tree, to my declarative programming. I've said I want 2 counters. And so React is processing the tree and called this counter function twice. Make sense? And then it does the work to make sure the DOM looks like the React element tree. And here's my 2 counters. And now anytime I want to add a counter, I can just reuse the function. Functions by default are an idea of reusability. I can call a function wherever I want, whenever I want, however I want, where I need it. And so React is choosing to define components as functions, functions that return a single React element. And of course, they could do other work inside of them. And then I can reuse this code as many times as I like without having to rewrite it, or what's called the don't repeat yourself approach, or DRY. This simple approach has proven to be quite powerful because other people can write useful components and you can just go use them. There's an entire ecosystem around React of useful components, work that other people have done, not even the people that build React. But also it's powerful for your own systems to build your own components or component libraries that you can reuse throughout a piece of software. Components are inherently reusable. At the same time, realize you won't always reuse every component. My app component, for example, well, there's only going to be one of those. But React has chosen that everything is a component. You're building your React element tree out of these. And that also helps explain again why we actually use react.createElement and pass app to it. App can't be a node in the tree by itself. It needs to be converted to a React element. And when React sees that the app function is that root node of the tree, just like any node, it knows it needs to call the function. Let's try that. I'll add another breakpoint in app itself. And so I told React the app function is a root node of the tree. It comes across app first and then begins cycling through the children. So first I should see the breakpoint in app, then the first counter, then the second counter. Make sense? So keep this clear mental model. React is calling your functions. Your functions return single React elements that may have children, and React will then do the imperative work to update the DOM to match your declarative statements of what the DOM should look like. It's time for a conceptual aside, and this is an important concept to understand how React expects you, encourages you to write your component functions. This is pure functions. Big word alert. A pure function. A pure function is a function that, 1, for the same inputs, always gives the same output, and 2, causes no side effects. Let's see what we mean. I'll start by creating a simple object. I'll call it counter and give it a property of name. And then I'll use a separate variable. Let's call it the counter value. Again, this is just going to be for explanatory purposes, just an example. I'm going to create a function that's just a pure function. I'll call it pure counter. It will take the object and the value And all it's going to do is log to the console. I'll output the value of name within the object, the space, and then the value passed. Then I'll call the function, passing it the object and the value variable. And I'll repeat that a few times. And the second time, I'll change the value. If we run this, we see that we got counter 1, then counter 2, then counter 1. This was expected. Note that whenever I called the function with the exact same parameters, the same inputs, I got the same output. Now, normally I might have returned this value. In fact, if I was to be more complete in exactly what we mean by a pure function, then I could return this value and then log the value of the return. That way, what I'm literally saying is whatever inputs come in, I'm logging the returned output. And I get the same value. The function is pure because it has no side effects. It makes no changes to any value outside of itself, anything that was created outside of itself. And for every set of possible parameters, the same inputs give out the same outputs. Now let's make a separate function that's not pure, that's impure. The first thing I'll do is mutate the value of the name property. I'm just going to append my name to the end. Then I'll also change the counter value variable, which is global. It's declared outside the function. Then I'll return the same as the previous. I'll put a little note here in the console just to separate the values. And I'll do the exact same logging. And then at the end, I'm going to log the value of the actual original global object counter. Let's see what happens. Well, this is a quite different result. I see counter Tony1, then Tony3, then Tony3. And you'll notice that the object now has the name property value of counter Tony. So this is an impure function. I've mutated the first parameter. I've changed the object, and the object is passed by reference, so I'm actually changing the object being passed in. And I'm updating the actual global value rather than the value that's been passed to me. In both of these cases, I'm causing side effects, I'm mutating values, and that means that for the same set of inputs, for example, this first call and this third call to not pure counter, I don't get the same output. That is Tony1, then Tony3. It's inconsistent. It's unpredictable. And as you can imagine, that could lead to difficult bugs. Impure functions tend to make buggy, difficult to manage code. When we're dealing with an application built up of functions, like a React application, it's much better for those functions to be pure. So much so that React has some features to help try and ensure that our function components are just that. Remember how when we saw the component being executed, the function being called by React, it passed something called props? Props are a fundamentally important aspect of React and React components, but all they really are the arguments to functions. We've already said that when React is looking through the tree and it sees that we've attached a function to the tree, a function component, it's going to call the function. But you may have been thinking, wait, we usually don't just call functions by themselves. Functions often can be passed arguments. Functions have parameters. I can give a function an argument, the parameter gets that value, and then I can use those values inside the function so that the function may not do the exact same thing depending on what arguments you give it. That's basic coding. And since React is using functions as components, the same is true. What's passed to the component, to the function when the function is called props. Let's imagine, for example, that the props we're passing to this list component are the number of list items that should be generated. Then when React calls this function, if I said 3, then the function component might be coded to return 3 li elements. If React calls this function with a 1, then perhaps I coded my component to return a single li. In this way, the same function component can be used multiple times, but generate different subtrees depending on the props. And it also might engage in whatever other unique behaviors according to the props it might need to. This makes components fully flexible and fully reusable. So far, we've been using React.createElement to create React elements. And we've had a lot of comma nulls after we pass the type. What's going in the comma null is the props. That is to say, the object that contains any of the information we want to be passed to the function. Let's try adding some props. For example, I'm going to add an object in each case. And what should we do? Well, let's say I want to give each counter its own name, which I'll display in the header. I'll say name, let's say 1. And in this other counter's case, I'll say name 2. Notice that I'm really only passing one thing, an object. That object could contain various properties. So I can pass various things to the function by including them in the object. But I'm only ever passing one object, because React is only really calling the function passing that props object. Let's try to figure out what's happening. I'll just call it props here for now, and I'll log it to the console. I'm not doing anything with the props yet, but we can already see them here. The 2 times that counter is called, they're outputted to the console. And this is all going to happen before React does the imperative work of actually updating the real DOM. So that's why they're at the top. If I open it, I can see my property in both cases. That is my first call to counter and my second call to counter, which React is doing. If I go to the sources and step through the code, I'll go to where it calls counter. I'll go down to the call stack, and I'll see in the render with hooks call, when it actually executed my function, it passed props. And there they are. The props were stored as part of that React element, and so it passed them to the function when it called the function. If I go again, there's my second call. And again, if I look, I can see the second call to the function passed that second props object. Then after these functions are called, React has a complete tree to then compare to the DOM and update the real DOM to match. Let's try using our props object. But instead of dealing with it individually, I'm going to destructure the object, using just the JavaScript feature of being able to split up an object into individual variables. I do that by using my curly braces, and then I'll put name. That's the property name in the object. So what I'll end up with is a variable of that name, which holds the value of that property. I'll do something simple here and just say that there's a second text child of the h2, and it's that variable name. And that works. Counter 1, counter 2. Article has an h2, which has 2 text children. There's no carriage return between them, no BR, so they just appear next to each other like that. And the same was true for the first one, which had the different prop. So I've reused my component using props. I've indicated an object that contains some information to be passed to the function, and in the function, I specified how to use the props. Now that said, there's one more very important thing about function components, about what React expects of a function. Let's change this. So I'm just taking my entire props object, props.name in this case, since it's inside the object. And then I'll try doing something like this. And this is a bit of a surprise. It didn't update. It kept the original prop values. Let's try stepping through the code for a second. I refresh, and I see the props. Currently, the name is 1. I try updating it, and when I move to the next line, I can see here in the browser that props still has a name of 1. This line of code didn't do anything. It didn't update the props object. Why? Well, I know just from knowing JavaScript that it is possible to prevent an object from being changed. It's called freezing the object. In fact, I'll go here under watch, and I'll check and see if object.isFrozen, which lets me pass an object and see if it is frozen. I'll pass it the props object, and look at that. The props object being passed to the function is frozen. So somewhere inside React's code, it's freezing the props object. It's saying that this argument to the function cannot be changed. It's immutable. Big word alert. Immutability. That is something that's unable to be changed. It's immutable. JavaScript objects can be immutable. And if the object being passed to the function is immutable, then we're assuring that the function is pure. React wants immutable props that cannot be changed to ensure that the function is pure. Now, there's other reasons and other ways to make the function pure, but this is part of it. If you could change the value of props inside the function, then you couldn't be certain that you would always get the same result from the function whenever you pass the same props. By ensuring that props are immutable, React is making an opinionated choice. It's forcing you to write your functions in a more pure way because it helps React to behave in a more predictable way, and it makes your apps less buggy because your components behave more predictably. You can't accidentally change the props in the function and cause a problem that would be difficult to ascertain what was really happening and could also make it more difficult for React to figure out how it should update the DOM. This is a choice by the folks that made React. Let's prove that this is happening. I've already been digging into the code of react-dom.development.js, where we see the imperative code for updating the DOM. But where might we find the proof that React is freezing the props object being passed to the component? Well, I need to go where React is defining its more core elements, where the React element itself is defined, perhaps. That's over in react.development.js, where React's core code, the code outside of even the DOM updates, is stored. I'm going to search for the word freeze, because I know object.freeze is a way to make an object immutable in JavaScript. This doesn't look like the right place. I'll keep looking. And look at this. I found a line of code that freezes an element's props. Let's see what it's inside of. It's inside of the place where the React element object is created. So when I create a new React element, I'm creating a new one of these. This is going to return the element object, and it has the things we saw before: type, props, everything that's on a basic React element. Here it is, the React element POJO. And if I scroll down, I find that it freezes the properties. So there it is. It made props immutable. Now I want to note again, when you go looking for this, the exact line where this code is may be different, and that's okay. The point is that you not be afraid of digging into the source code of the frameworks and libraries that you're using, so you can understand what's really happening and not be surprised when something doesn't work the way you were expecting. And one other thing to note, remember we said we could destructure the object. That means that I'm pulling out the individual properties from the object and putting them in their own variables. But then that means that the variables themselves are not frozen. Only the original object was. So if I do it this way, then it does change the props. And that's actually a bit dangerous. So that's a warning for you. Destructuring the props is useful, but be careful about mutating the props. As in this case, I expected to see 1 and 2, but because I mutated the props, the component didn't behave as expected. And when you get into a large, complex tree of components, this can cause you a real headache. That said, again, destructuring can be useful just for making it easier to deal with the props inside the body of the function. When later we get into writing more complex React applications, passing props down through the tree, various children and grandchildren that are our own function components, becomes an important aspect of how we write our React applications and how we help keep them maintainable. For now, we're just trying to understand this basic concept. Our function component is called by React, and it passes the props that are stored on the React element object itself. Remember, this POJO that is the React element stores the props. And if it calls the component as a function, it passes their value. So far, we've seen how to build trees of React elements and then ask React to update our DOM to match. But we've only been doing that in a very static or unchanging way. In real applications, we need logic. We need to be able to decide when to show certain things or not show certain things, when to update the screen. We want our applications to be dynamic, to be changing, and to respond to our inputs. So how can we do that? And how will React deal with updating the real DOM to match? This is template logic. Since our React application is really just made up of functions, what we're calling function components because they return a single React element, I can also simply code logic in order to decide which functions to call. So for example, let's suppose that I had two different versions of my counter component. I'll make the change very simple. I'll just change the text inside the paragraph in the second one to a different format of how to express how many times were clicked. This still isn't interactive. And I could do this better simply by changing this string, but this will be a good example of having two separate components that I then want to swap. Up in my app function, I'm going to actually just have a single counter instead of two, but I'm going to change which counter component I use, this first one or counter 2. To do that, I'll need to set up a bit of logic. So let's just make a variable to have our logic work around. I'll just set a string called counter name, and that's what I'll pass to each of these counter components as props. Then I'll use a ternary operator and say that if the counter name is 1, then I'll call my first function component. I'll set up a props object where name is equal to this counter name. But if counter name is something other than the value 1, I'll do another create element, but I'll use the second counter. So I'm creating a child of section, but that creation is wrapped in some logic. Section will either get the counter function object as a child or the counter2 function object as a child, either one wrapped inside a React element. So counter or counter2 would become the type of each of these React elements. Now, because counter name is 1, I should see you clicked 1 times because this logic will say, well, use the counter function. Again, I'm just passing this as an argument to the create element function. So either This will be passed as an argument to create element for section, or the counter to one will be passed as an argument to create element section. Simple logic. And there it is. You clicked 1 time, and there's the name of my counter. When I look in the console, I see that code we added to the React's code itself. When I look in the console, I see the console.logs that we added to React's code itself inside react-dom.development.js. And it's still behaving as expected. The entire section is being appended to main. This whole set of the DOM is created at once. Now I want to let me, the user, change the value of counter name. Now again, we're thinking declaratively. So ideally, I would just be able to change counter name, and React should then update the DOM to match. We'll do this in a very simple way. I'm just going to add a button, and it will have an on-click event. Now, this isn't anything to do with React. This is just basic JavaScript and the browser APIs. I'll call an update function. And then here in my JavaScript code, I'll just make this update function, and it will set this global variable to a value of 2. I'll make sure that it's running. There, let's try it. Now I have an update button. I'll click it. It does run. I see updating, and nothing happens. Did you expect anything to happen? Well, notice that this variable, although being used inside my React-based functions, is not somehow automatically connected to the React app, because I just declared it as a simple variable. I didn't use any kind of React tooling beyond simply using it when I created the props. React is just going to run these functions, update the DOM, and it's done. Nothing has told React that it should respond to this value being changed. Nothing has told React to re-render, to recreate this tree, to recall all these functions and see what's changed. If we're thinking declaratively, what I want React to do is to simply recreate its own tree of elements, look at the existing DOM, and then update the DOM to match. Let's force that to happen ourselves manually. And later in the course, we'll see how to use the tooling that React provides, its features, to cause a re-render. So let's rename this function re-render. I'm going to manually ask React to render again. But after I've changed this variable name that I'm using in the logic. I'll use this exact same call, root.render, so that it will then go and call counter or counter2, create the tree of React elements, and do what it needs to do. So when the app first loads, it will load counter. Then when I click the button, I'll change this value to 2. So this logic, which is simply logic inside this call to the function, will instead create an element from the counter2 function object, which means that this P's child, this text, will be different between the two different React element trees, the original and the one after I click the button. I'll change this to re-render, and we'll see what happens. Nothing so far, and then I click re-render. And hey, that worked. React recreated the tree of React elements and updated the DOM to match. Note that the name changed, and we can see that we're using a different counter, counter2, because the text inside the P changed. But notice something interesting. After my re-render, I get appending child instead of appending child to container, and I get this article. Try it again. Yeah, so article has been appended, not section. Let's look at that. Inside main, originally, the section was appended to the container of the app. But instead, on the re-render, only this article, which contains the to and the times clicked, was appended. That's interesting. So why would this happen? Well, the H1, the section, these other parents haven't changed. So if we were writing the imperative code for React, it would make sense to try to be smart enough to look at the existing DOM, to look at the React element tree, and if the existing DOM already matched in certain places, to not bother doing the work of updating that part of the real DOM tree, because updating the real DOM tree is an expense. It requires work on the browser, it can slow the app down, etc. So React was smart enough to only append the portion of the real DOM tree that was actually needed to match the virtual DOM. But there aren't two articles here, so it's more than just an append. Let's go back to the React DOM code, React's imperative code for updating the DOM. And I've already put some console logs for append child, but I also know that there is browser APIs for removing DOM nodes. If I scroll down a bit, or if I did some searching, I would find remove child and remove child from container. So I'll go ahead and just add the same kind of log so that I can see when React is also removing a child, and I'll throw on when it removes it from the main container. And then I'll just say container, and I'll log that too. Both of these are parameters that are being passed within React itself. Again, I'm never actually using these functions myself, but let's see what happens. And there it is. After I re-rendered, React recalled all of those functions of mine using the logic. So instead it called counter2 the second time instead of the first counter component, which means it got a slightly different looking React element tree, a slightly different looking virtual DOM. It looked at the existing DOM, which already had elements in it from the initial render, and saw that the fastest way to make the change would be to remove the article that had the counter 1 and the you clicked 1 times, and then append a new article real DOM element that had as children counter 2 and times clicked 1. It didn't remove this entire section, but just the DOM element that was necessary to update the real DOM to match. It removed one article and added the other. Pretty smart. So now we've learned a few important things. React has the ability to look at the existing DOM and to make intelligent changes about how to update it. And that includes if we recreate or re-render our entire virtual DOM tree, our entire tree of React elements, and give it to React again, it can simply compare the two trees and make the change. Notice that the first call, this first call to render, and the second call really didn't have anything to do with each other. They were full, complete calls. The entire React element tree was recreated each time render was called. App had to be called, then either counter or counter2, and all of these create elements were called again as well. But that isn't a very expensive process because the React element tree is very light and simple. It's just plain old JavaScript objects. In each case, each time React rendered, it looked at the current DOM tree, the real DOM tree, and updated it to match. In the first render, for the real DOM tree, it had to add the entire set of DOM objects from this section all the way down. But on the second render, it realized that it only needed to swap the article element. And this happened because I was able to just insert logic into my template, asking a different function component to be called depending on some criteria. And I'll say it one last time, it's not that this little portion of the React element tree was changed. It's that the entire React element tree was created twice. One of them would have counter as a child, and the other would have counter 2 as a child of this section element. And then React did the imperative work from there. I'm manually causing React to re-render, and this is not the way you would do it in reality. But my goal here right now is to piece by piece help you to build a proper mental model to help you to understand. Later, we'll see how we should do this in reality. But for now, I just want to make sure that your mental model is accurate. We can put logic into our React element tree creation process, and React doesn't have to render just once. React can re-render over and over again, rebuilding its entire React element tree over and over again, and then update the DOM each time as needed. We've seen how we can pass props to our own function components. That is, when React calls the function, it will pass that value, that object, to the function. But what about all those React elements that come along for the ride with React that we already saw? This is element properties, and it will connect to attributes in the DOM. Let's go back and simplify our app again. I'll get rid of all this logic, and we'll just have a call to counter. I'll get rid of the re-render and the counter 2. I'll get rid of this button, and I'll get rid of the reference to the name. I won't even pass a prop here. We'll just make it very simple. When I run this, I just get, again, just this basic version. Counters, a counter, I click 1 time and a button. But here's a question. Let's look at this button. Notice that it doesn't have any attributes. For example, the most common attribute we add when creating a web application or website is usually a class to make this particular button selectable in CSS and to give it particular styling. Problem is, React is the thing in its imperative code that's adding this DOM element. So how can I tell React that, for example, I want a class or some other attribute? Well, let's stop and think about this create element call that takes strings. React has to know how to create each of these DOM elements. In fact, let's take button. I'll go into React DOM and I'll search for button. And if I look around enough, I actually find lists of supported tags. That is to say, types of elements that React knows how to create. And there's a bunch. And it may have certain rules around them to make sure that they conform to the HTML standard. But this makes sense. If it's not my function component, if it's React's, then it needs to know how to create each type of element. And when it creates that element, using the DOM, it should be able to also add attributes using the browser API. For example, I grabbed this root node at the top here. Using the browser API get element by ID. So now I have the root, which is main. Outside of React, just using the browser APIs, I can say .class name and give it a CSS class name. I'll just make one up here. Now, when I go and look at my main, there it is. So what actually happened? Well, if I had been writing HTML, I would have put class equals root on the element, and then the browser would have converted that into a DOM element object with that property and name. Since I did this using the browser API, which allows me to update the DOM element in JavaScript, I had to use the property name that the browser provides. It doesn't provide .class, it provides .class name. The word class was avoided in code. And this makes sense these days, as class is actually a reserved JavaScript word. You can create classes in JavaScript. So I had to use .className equals root. Now, when the browser shows me the DOM, it shows me it as if it was HTML. So it converts it back to what I would have written had I been writing HTML. So that's why I see class and not class name. But what if I want to add a class to a DOM element created by React? Here I'm creating the React element, and I know that a real DOM button element will be created by React's imperative code. Well, remember this second parameter that's always null is actually the properties being passed to the function. And each of these elements are calls that React will actually make itself to its own functions to build these React elements. So I can do the same thing. I can essentially pass props to pre-existing React elements. For a button, I can say class name button. React chose to match the existing browser API property name. So it didn't say class, it said class name. So just like in the case of my custom function component, I'm passing a props object where the property name on the object is going to be the attribute name, and the value of the property in the object will end up being used as the attribute value. So if I put class name button on this button React element, when the equivalent real DOM element is created, if I go and look, there it is, class equals button. And just one more time, remember what's really happening here is that I'm creating a simple JavaScript object. I've passed props to React to tell it that I want these properties to be applied to this simple JavaScript object. And then later, when React updates the real DOM to match, it will look at the properties of this simple React JavaScript element object and create a DOM object, a real DOM object with attributes that match. In fact, I can just add other properties, let's say name Tony, and they'll show up as attributes on the real DOM element. I'll undo that. Make sense? So rather than imperatively adding the attribute to my DOM element, I tell React what I want the DOM element to look like by passing props to the React element. And then React does this imperative work of creating the DOM element accordingly. So we're continuing to get a mental picture of building up a user interface declaratively in React and the imperative work that React is doing. Now that said, as this gets more complicated, this approach to declaratively saying what the React element tree should look like becomes cumbersome. And that's one of the reasons why I said this is not the way that you should be doing things. In the next section, we'll now introduce the style of declaratively defining the React element tree that you're likely used to seeing if you've looked at any React code. It's a style that can cause confusion, especially for those new to React. But it does make sense, and you can get used to it quite quickly. We'll see how and why in the next section, which is on JSX. In this section, we'll dive into writing React in a way that will look more familiar, but that seeming familiarity can trip us up. In order to avoid some mistakes, we need to understand what it really is and how it really works. And what we're talking about is JSX. It's time for a conceptual aside. This is markup and tree creation shorthand. What's the first syntax that comes to your mind if I asked you to code up the contents of a tree? That is, some data that's part of a tree data structure. Well, we've already been doing that with arrays and objects, but the most common way is one that you've likely done before. That's right, markup. Whether it's XML or HTML, the idea of opening and closing tags with their contents, allowing us to define roots and parents and children, etc., is a long-standing way of defining in text the contents of a tree data structure. And then the computer can read that text written by the human and create the tree in its memory. So when you're looking at markup, you should be thinking in terms of trees. And since in a library like React, we're creating a lot of tree data structures, but we're doing it all inside JavaScript, the question begins to become, what's the best way syntactically to define those trees? That is, how can we make it easier for the developer, us, to write those trees and to make it easier for tools to help us write those trees? And as we think about that problem, our mind should then go back to what already exists. The idea of tags, markup, a shorthand for defining trees. If this is already a better way to do it, a way that's worked for decades, wouldn't it be interesting if we could continue this approach within our JavaScript code? And that is what JSX is all about. One more conceptual aside before we can fully understand JSX. This is transformation and transpilation. Big word alert. Transpilation, transforming, that is, changing the text of code written in one syntax and converting it into a different syntax that does the same thing. Sometimes a transpiler is referred to as a transformer, and they usually exist to make our lives, the developers, easier. We might be able to write the code in a way that's easier for us, and then the transpiler or transformer will look at our code, read it, and then change it into something that the engine, in this case the JavaScript engine, will accept. So if we imagine a transformer or transpiler within React, and we wanted to be able to define our element tree the way we normally might using markup, well, we know that JavaScript doesn't allow markup. It doesn't support it. It's not part of JavaScript syntax. So if we wrote markup within our JavaScript file to define our tree data, we would need a transpiler or transformer to look at our code and then change it into something that JavaScript recognizes before the code is given to the JavaScript engine to run. So again, transformation, transpilation, is just helping us to write things in an easier way, and also potentially helping the tools that we use to write the code to provide more features that make us more efficient as we're typing. In this lesson, we get into how we create React elements using JSX, which is really just shorthand for creating POJOs. To get started, we'll go straight to the source, the primary source of understanding what JSX is, the JSX specification. When we say a specification, we mean a document or series of documents that describes how something works. And it's official, meaning that Facebook, which created JSX, has created a specification to say how they will implement JSX, a transformer or a transpiler that is, and how anyone else who's building a transformer or transpiler for JSX should work. That is, what is valid JSX? What does valid JSX look like? But specifications also commonly give us more than that. They give us some behind-the-scenes thinking behind why something works the way it does. Also note that even though Facebook created JSX as part of React, it was separated into its own specification. And that's because really it's just a generic way of building up tree data structures using markup as part of a JavaScript file. So that means other libraries, other frameworks could also choose to use JSX, and that is exactly what has happened since JSX was introduced. React is not the only JavaScript framework out there that uses JSX to define tree data structures. Now let's look at what the specification actually says. It says that JSX is an XML-like syntax extension to ECMAScript. And that means basically that JavaScript does not support writing markup within its code, and markup being XML-like syntax, tags. And of course, ECMAScript is the proper name of what we normally refer to as JavaScript. Now, it also says without any defined semantics. What does that mean? Well, we can compare it to what the HTML standard says regarding the semantics for its elements. It says that elements, attributes, and attribute values in HTML, and this is the HTML specification, have certain meanings, or that is to say, semantics. And that's all semantics means, meanings. For example, the OL element represents an ordered list, and the lang attribute represents the language of the content, etc. So when you write or author HTML, you're expected to use elements that correctly correspond to the content they contain. If you're marking up an ordered list, you should use an OL, not some other element. JSX, on the other hand, doesn't have any defined semantics. You're creating your own tags, or the JSX tags are being converted into something else that does have semantics. So be careful. Sometimes you'll see people say that JSX is HTML inside your JavaScript. It's not. It's a markup language with no semantics. It's just a shorthand for building up trees of information. And JSX is not even intended to be within the browser engines like JavaScript is. It's intended to be used by preprocessors, another way of saying transpilers, to transform these tokens, and by tokens we just mean the text, like a tag, into standard ECMAScript. So in other words, we take tags and convert them into JavaScript that the JavaScript engine will accept. Here's an example in the specification. I have a variable equal to some markup. Now, I'll admit, the first time I saw JSX years ago, I, like many others, was turned off by it. It just doesn't seem right to have markup inside your JavaScript. But once I came to understand what JSX really was, it helped a lot. JSX is just shorthand. It's just helping me to do my job faster. It's not what's being delivered to the JavaScript engine. And of course, one of the best ways for me, the coder, to write down trees is to use tags, is to use markup. It's been that way for decades. Now, I'll skip the actual definition of JSX, which is quite short. And it also talks about how the choice was not to put all of this in strings, but instead to make it easier for tools to help us. So instead of wrapping this text in a string, JSX is introduced as an entirely new type of primary expression. When it says primary expression, that means that it's extending the words that are allowed to be used within the JavaScript programming language. So a JSX expression is a sequence of markup that may have some standard JavaScript in between and can be included as part of normal JavaScript, which will then be transpiled into complete normal JavaScript, no markup. The note here says, don't you love the syntax highlighting? Because it's not a string, but a proper expression, that is to say, words that are part of the accepted language, we can do things like highlight the tags. This, again, is just about making our life as developers easier. Sometimes people ask, what does JSX stand for? Well, it kind of stands for two things. It's a JavaScript syntax extension, meaning that JavaScript already has its syntax contained in its own specifications, things like the word let, or var, or const, etc. And we're extending the JavaScript syntax to say, well, within a JavaScript file, we can also write some markup. Another way of thinking about it is that it's JavaScript XML. It's markup language inside your JavaScript. Either way, it's JSX. Now, going back to the code that we've already written, remember that this code is creating tree data structures. The first React create element is the parent, and inside of it, it has an H1 and another section. Those are children, and then a grandchild called counter inside section. But you can already see that it's kind of tough to keep track. What's the parents and children and grandchildren? What belongs to what? Where does it end? Which comma belongs to which function call? It's not impossible, but I wouldn't want to have to do this all the time. It's made my life as a developer less easy. So what if here, where I'm defining React elements, a tree of React elements using function calls, I could instead just write markup, JSX. I have a section in H1, a section, and a counter inside of it. So I'll go ahead and replace this with a section. Inside that was an H1 with the word counters, another section, and inside that was a function component called counter. So remember, we said that JSX has no semantics. I'm essentially just saying I'm creating a tag. My function is being called as its own tag, and that's allowed. You can create any tag names that you want in JSX, at least according to the rules of how you can name a function in JavaScript. This is already much clearer and easier for me to keep track of, even if at first, if you're not used to this, it feels a little strange. What about down in the counter component? Well, I have an article at the root, an H2 with the word counter, a paragraph with you clicked 1 times, and then a button with the phrase click me and the class name property set to button. So what would this look like if I was using JSX, just markup? Well, article is my root. I had an H2 with the word counter. I had a paragraph. You clicked 1 times. I had a button. And the attribute name is the property name that we were using as part of the object when we were creating the React element. So it's class name, not class, though you might be used to the word class in markup in HTML. And then I'll say click me. Already our understanding of what JSX really is helping us, because a lot of people complain about having to use class name instead of just class. But we understand that this is a JavaScript syntax extension, and so that's why. This is not what's being sent to the browser, but that object creation is. And for creating the DOM element, React has chosen to match the name of the DOM element attribute for the React element attribute, as we already saw, class name. I'll get rid of this here. Now, what happens if I run this? What do you think will happen? Well, nothing. I get an error. Uncaught syntax error, unexpected token, and then the very beginning of my markup. And that's expected. JavaScript doesn't support this syntax. I need a transpiler, a transformer, a preprocessor to change the text of my code before the JavaScript engine does its work. I'm going to copy all this code, and let's go take a look at one. This is Babel. I can go to babeljs.io and try it out. Here I can drop code containing JSX and see what code comes out of the transpiler. So I'm going to paste the code that we just wrote. And look what we get. We get my function and the return, and then the beginning of a sequence of React.create elements that looks just like what we were doing ourselves. The transpiler has read the text of my code and converted it to something that JavaScript can accept, that can run. Same thing with my counter function, including my attribute that got turned into a property on this object being passed to create element. Now, here's what's even more interesting. Remember, we said that you shouldn't use create element yourself. That was just for explanatory purposes. That's because this is the old way of creating React element trees within React. If within Babel, I switch the React runtime from classic to the latest, the actual code that's generated by the transpiler or the transformer is different. I see my return, and instead it's a series of different function calls to a different set of functions. Over time, React has improved the way it creates React element trees. And so the latest version of React will use this approach to creating them, a different set of functions that do things a bit differently. But notice I didn't have to do anything to my JSX to gain the benefits of these updates within React itself. So that's a good reason to use a transpiler. It allows the transpilation itself to keep my code more up to date. If I had been writing my own React.create elements, then I wouldn't be able to take advantage of the latest and greatest things that are happening within React for creating element trees. Either way, when you look at JSX, you shouldn't see markup. You should see something that ends up looking like this. Function calls an object creation, and it's directly being turned into JavaScript. That's very important because it helps us avoid some pitfalls. To understand that, we need to actually have our app work by transpiling this content. Now, again, later in the course, we're going to get into how we'd really want to do this in a real production environment, in a real app. But here, for educational purposes, we've continued to use this inline version of React and React DOM, which means we'll also use an inline version of Babel. That will just make things easy and quick for us for now. And then I'll go to the Babel website to see what the JSX is being converted into. I can drop this script before my code, the code from my app.js file. And then this JavaScript is going to look at these other JS files based on these script tags in the DOM, read the contents of the code, and then make the changes before the engine can process them. Now, that's actually going to be happening inside my browser, which is why you probably don't want to do this in real life. You're adding a lot of extra work to your user's browser to first transpile the JSX. It's better to transpile the JSX before it's given to the user. And we'll talk about how to do that later in the course. For now, we know that Babel is going to take all of this and do exactly what we saw when we tried it out. So we try running it and, we're still getting an error. Well, that's because, in this case, because I'm doing it on the fly, I need to tell Babel that this script tag is JSX. When it looks for script tags in the DOM, it looks for script tags that have an attribute with type JSX. You wouldn't have to do this in a normal production environment because we would have already converted the JSX to just regular JS. And there we go. There's all our code. And it even warns us, you're using the in-browser Babel transformer. Be sure to precompile your scripts for production. In other words, convert the JSX ahead of time and save all this work on your browser, your poor user's computer or phone. But everything looks to be working. That means that all of this JSX was converted into JavaScript code, into acceptable JavaScript code, and then run. So essentially the same thing that was happening before is happening now. The JSX is just helping me, the developer. It has nothing to do with what the browser and the JavaScript engine is processing. Now, knowing that this is actually JavaScript, that it's being transformed into JavaScript, helps us avoid some bugs. For example, maybe I just don't like how this looks. I want my HTML to look like that. Oh, interesting. Did you see how this just went dark in Visual Studio Code? If I hover over it, it says unreachable code detected. Why? Well, let's take this, put it into Babel, and we see that what's actually happening is this return statement. Because JavaScript doesn't require us to type semicolons, it has what's called automatic semicolon insertion. This return statement is being processed as its own line, the semicolon at the end, which basically means the function is just returning. Everything after is not being reached by the JavaScript engine. That's true with app and that's true with counter. So if I save this and go back to it in the browser, I see that nothing has happened. I don't get any errors. It's simply that this app function returned nothing and this counter returned nothing. So you need to imagine this JSX as all of these function calls and object creation within JavaScript syntax. If I wanted to do that in JavaScript, I would simply wrap whatever I was returning in parentheses. And I could even tab this over because the extra white space won't mean anything. That is a little bit easier to use. The tool now can tell me, yes, the JavaScript will get run right here. And because Visual Studio Code is understanding the JSX, it's doing that work. There, it lit up. I'll tab it over just so it looks really nice. And now this should work. Let's see what happens. It does. Because what's the JavaScript actually being run? Well, when I update it, I can see I don't see that semicolon anymore because these parentheses have told the JavaScript engine that I'm returning an entire expression here within the parentheses. I'm no longer hitting the bug of accidentally returning early from the function. This may have been counterintuitive if we didn't really understand what JSX was. But because we do, it's pretty clear, don't you think? If it's not clear to you, take some time copying and pasting JSX into Babel. Get a feel for what it's doing. Start to train your brain to think of JSX as future JavaScript code, because that's what it is. And now I'm able to write my components using Markup. Now, we said there's no semantics, but section, H1, article, those are HTML elements. So don't they have semantics? Well, yes and no. When this article element, the React element, is used to create a DOM element, that DOM element will have semantics. So we do have to think about semantics because ultimately we're creating DOM elements, which need to follow the HTML specification. If I have an ordered list, I should use an OL inside my JSX. But I don't need to worry that counter needs to have some kind of semantics. It doesn't. At the JSX level, there's no semantics. But for the elements that come along for the ride inside of React, the elements being converted into DOM elements, we do need to think about semantics. We're just a step away from that DOM creation. React is doing the DOM creation for us. So you can think about this as a set of instructions of how to create and update the DOM. Make good HTML choices, but you also have this flexibility to create components and name them what you want. In the end, I'm still looking at something that looks like Markup, and it's helping me and the tool that I'm using to make my development life faster, more efficient, etc. I have a very readable way to specify the contents, the data that's part of this tree. And from this point forward in the course, we will define our React element trees using JSX. Let's continue our discussion of JSX and realize that when we start to add logic into our JSX, things for those that are used to writing HTML can start to look even stranger. But if we understand and keep in mind what JSX really is, then we can take advantage of the ability to have logic alongside of our JSX, as long as we're thinking in React elements. Most apps aren't going to be as simple as the one we've been building. They're going to have things that you'll do based on conditions and logic. If this, then do that, etc. We also tend to break out our code into variables and functions, etc. And that can feel unnatural when dealing with the syntax extension to JavaScript, where we're now adding markup directly into our JavaScript code. But if we keep in mind always what JSX is being turned into, then we can realize that it's pretty powerful and we can do some pretty neat things. Let's go, for example, back to the case where we want to re-render our app when I click a button. And I'll have some logic to show one version of the counter versus the other. Going back to my index file then, I'll add back a little style for a button and a manual re-render button, which we would never do in reality with real React applications. But again, we're on our way piece by piece building up what we need to know. Going back then, I'll add a variable which we'll base our logic on. Counter name, say 1. And then a re-render function that's being called when that button is clicked that changes that name to 2. I'm going to pass that counter name as a property, props, and I'll reference it inside my JSX. Now, hang on a minute. How did I do that? Well, JSX, according to the specification, allows you to inject actual JavaScript code inside of your markup code using curly braces. That's necessary because it's really hard to tell for the transpiler if you mean something to be JavaScript code or if you mean something to purely be text. For example, if I just said name, how would I know whether I meant the word name should appear or this variable's value should appear? In this case, I'm deconstructing the props, setting a variable name of name equal to whatever that value is inside the props object. And so I want to be sure that the transpiler knows I mean This inside the curly braces is me writing JavaScript, not text. So anytime you write JavaScript inside of Markup, inside JSX, you'll need to add the curly braces. And just imagine yourself telling the transpiler, there's some JavaScript here, even though we know that the markup actually is JavaScript too, but the transpiler is creating that JavaScript. This is JavaScript that I'm writing directly. Now let's take this entire function. We'll make a second version that will just have different text. This way we can tell the difference between one is called and the other. Now we need to say, if counter name equals 1, show this counter. And if it equals 2, after I click the button, then instead show counter 2. That is, React should call the counter 2 function, update the DOM, etc. Now I could do that more verbosely here, but I also just want to show something that looks strange at first if you're not used to JSX. I'm going to declare a variable, counter1, and I'm going to set that equal to the tag counter and pass as props the counter name, and then a semicolon at the end. And I'm going to do the same. Const counter2 name equals counter name. So let's break down what I've done here. This might look strange to set a variable equal to a self-closing tag. JSX allows self-closing tags. That means there's no children inside of it, so I can simply end the tag without doing a second /counter. But I could do that as well. Either way, this may feel strange to say a variable set equal to a tag. But remember what the tag is. The tag will be converted into JavaScript, something similar to React.createElement. So what I'm really doing is setting a variable equal to what's returned by whatever function is called, essentially the function created by this less than and greater than signs, the tag itself. That will become a function call. It's not set equal to my counter or counter2. What I'm doing is I'm saying counter1 is equal to some call a function within React, telling it React eventually, if we reference this variable, call my counter function. Same thing here, counter2 is being set equal to some internal React function call where I'm passing to it my function counter2, as well as the properties that should be passed to the function when React calls it. When React does call the function, it will pass a props object where a property on that object will be called name, and the deconstruction here will pull it out and set this individual variable equal to the value of that name. Now, how do I do my logic inside of the JSX? Well, note that instead of just counter, this is already done for me. The variable is equal to this React function call. So I could just put it here. But that would be text. If I actually run it, there's the text. Let's see what this would transpile into. I'll go over to Babel, drop this in, and let's find my section. There it is, down at the bottom. It's a React function call passing the type section and saying that it's children, and then the child is just a string, counter1. So I've created a child string. If instead I tell the transpiler, this is JavaScript, I wrap it in curly braces, it's still a child of section. But now, if I transpile it, we can see a very simple change happen. Section is still the type, and children is not string counter1, but the variable counter1. And the variable counter1 is up here. It's a React function call passing my function object counter and the props object with the name. So now children is set equal to that. So now children is set equal to the results of this function call. And we know that it's actually JavaScript that's going to run and not a string. If I want some logic, for example, I want to say counter name, if it equals 1, then use counter1. Otherwise, use counter2. If I look at what that transpiles into, I can see again, just some JavaScript. Whatever was inside the curly braces are removed by the transpiler, and it's just a reference to what the children property is. The child of section is some JavaScript. And that's what you should imagine when you see something like this. The child of section is this piece of JavaScript. And this will turn out to be either one call to one of my function components eventually, or the other. Let's watch it work. Here's the very first counter1. You clicked 1 times. I'll click re-render, which will change the counter name to 2, request a re-render. The tree of React elements will be re-rendered, and this time counter2 will be the child of section instead of counter1, and React will update the DOM to match. Re-render, and there it is. Counter2 times clicked 1. This worked. Again, this at first can seem a bit strange looking, but trust me, it can become very natural, especially if you think in terms of the transpiled code. If I drop all this code in here, let's grab the transpiled version and take a closer look. The transpiler took my code, went out and got this JSX functions within React for the actual function calls that these tags are being converted into. In my app function, I see that counter1 is set equal to calling that function and passing my function object and the props. Same with the second one. And then it returns section with children h1 and section, and that section has as its child this JavaScript. So I should see the call to the React function, which really means this less than greater than, that's really what that's being converted into. And this closing tag, the set of tags, is being converted into this function, and the type is section, which is the type of tag. And then it passes children, which are further calls because it's other tags, h1. This case, it's text, see the string with just the quotes. And then another child section, which also has children, and then there's my JavaScript code. And then we see the same thing below. We see a lot of children with either function calls, string values, etc. And the same with counter2. So if we're looking at our JSX and thinking in terms of the less than greater than, starting ending means call a React function, passing the type, then lines of code like the counter1 and counter2 feel much more natural. But if we compare the two, which would you rather be typing yourself? The code that's actually being run in the browser, or the pre-transpiled code, the code that will be transpiled by the JSX transpiler? One other note, we saw that when we set an attribute equal to a variable or a piece of JavaScript, it also is wrapped in curly braces. So in this case, it's not a child, it's an attribute, but that means it's just going to be passed as an object. And so we're making sure that we don't mean counter name, the string counter name, but the actual variable counter name, some JavaScript inside these curly braces. We'll do more logic like this over the rest of the course, and a lot more in our final project. For now, I just want you getting used to the idea of thinking in terms of actual React elements and the code that React is generating. Then what you can do with JSX won't look strange. Instead, it will feel like what it is, a really great shortcut to what would otherwise be difficult to write code, which has been made much easier. It's time for a conceptual aside. In this conceptual aside, we talk about HTML authoring. We've already talked about how JSX does not have any semantics. That means the tags don't have an inherent meaning. But JSX, when being used to build web applications and websites, is ultimately making a tree that does have meaning, the DOM tree, the tree of elements that are predefined in the HTML specification. And as we saw there, each of those elements does have meaning. So here's the problem. When we get in then to authoring HTML, what we actually mean is looking at our content and choosing the most appropriate element to mark up that content. Out there on the internet, we often see HTML that looks like this. Both the div and span elements have no meaning, and yet they're tremendously overused. There are multiple problems with this kind of markup. One, it's less readable. It's more difficult to know at a glance what this content is. Another major problem is that it's less accessible. For example, those who use screen readers to read the screen to them because they're unable for some reason to view the screen will have much more difficulty with this kind of markup because there's no meaning to impart to the screen reader program. The program also doesn't know what this content is. The point of semantic markup like HTML is to provide meaning. So this markup misses the point. One last thing, it's not future-proof. In the future, who knows how we'll consume HTML documents? What other ways? For example, perhaps an artificial intelligence will consume the information in some way. Not having your markup well authored will only spell trouble for you down the road. On the other hand, carefully authored HTML is self-describing. It's meaningful. It's easier to read and thus easier to maintain. I often see JavaScript developers who focus so much on the JavaScript that they ignore semantic HTML. And that is a mistake. It should be a primary piece of your work if you're doing any kind of front-end web development. Not authoring your HTML well hurts yourself, your team, and your users. But it's very easy to fall into the trap of not authoring your HTML properly when using systems like React and JSX. Let's see why. Let's talk in this lecture about HTML authoring in terms of React, and we'll talk both about fragments and the div element. We've already learned that our function components return a single React element that has children. That means that when you're making function components, devs are often thinking about what's the root element of the React element tree, the subportion that's being returned from this function. In our case, we tried to do good HTML authoring, but as we said, a lot of devs never think about it. And part of the reason they never think about it is because the tutorials and education and examples they've seen don't think about it either. So devs tend to use the div element. They've kind of learned like it's some kind of generic container that they can always use anywhere. They may also use span in a similar way. Even though the markup doesn't need a wrapper, React needs the markup to have a wrapper. It needs to return a single parent element. And so we often see div everywhere. But that is a problem, and it's something I'm going to try to help you with in this course to avoid, for you to be better than the average React developer when it comes to your markup choices. Let's take a look at what the HTML specification itself says about the div element. I'm going to go to section 4, the elements of HTML, and I'll scroll down until I see the specification for the div element, the official specification. And it says that the div element has no special meaning at all. It represents its children, so it has no semantics. Not really. And there's a note, because div is so incorrectly and overly used. It says authors, that is people writing HTML, are strongly encouraged to view the div element as an element of last resort for when no other element is suitable. Use of more appropriate elements instead of the div element leads to better accessibility for readers and easier maintainability for authors, as we said. And the same thing is being said by the HTML specification itself. So that means we shouldn't just use div as our first tool, but we should use it as the last possible element that we could possibly need. Now, let's imagine that I was one of those kind of developers, putting divs as my initial return everywhere. There is another problem. It's not just the fact that the div is the inappropriate element to use in most cases. The other problem is the depth of the DOM tree being created. If I inspect, I can see that I have my main, which is where I've mounted my application. That is, that's where React is going to start adding and editing DOM nodes. I have a div, so that's an extra layer on the tree. I have my H1 and a section, and then inside the section, I have another div, which is just another layer of the tree. And then my actual component information, the part that I want the user to see and interact with. So essentially, I've added 2 extra layers, extra levels to the DOM tree that don't actually really need to be there. I have them there because, well, my React function needs a parent component. And this is actually an issue not just with readability and how hard it is perhaps to maintain, it's also a performance issue. The deeper your DOM tree, the slower your web page. More DOM elements, more things for the browser to look through to try to figure out how to lay out the page, and also the slower your CSS. The CSS has to essentially search the DOM tree for elements, so the deeper it is, the more elements there are, the slower that will be. I've often seen JavaScript developers be very concerned about the performance of their code while they wildly add layers to the DOM tree, hurting the performance without caring, or more accurately, without knowing. I don't want that to be you. So if we have these deeply nested, unnecessarily large DOM trees, because we're thinking solely about trying to build our components in React and not about the final DOM, which is what you should be thinking about, how can we fix that problem? Well, for starters, we're thinking more in terms of semantic HTML. So we're not using divs and spans by default. That's good. That means when the screen reader looks at this, it knows it's a section and not just who knows. It knows this is an article. But those aren't even really fully necessary in this application. I, as an HTML author, could say, well, I actually don't need these elements. They're not helping any. The H1 is sufficient and the H2 is sufficient to segment these off as their own pieces. Now, maybe I do want the article and section. That's up to you as the HTML author. But if I know that I don't need the DOM tree to be any deeper than what it is, what can I do? Let's go back to the JSX specification. There's something in here to help us with that. If I scroll down to where all of the valid things that JSX can have are, for example, in opening element, closing element, we saw a self-closing element, which has a slash there and just a single tag. There's another thing called a JSX fragment. It's the normal less than greater than with an ending tag, but no type. So what happens if we do that? It's allowed according to the JSX specification, a fragment, essentially a call to create an element with no type. What will React do with this? Let's see. Everything looks the same. And if I go to my main, I see, well, look at that. Immediately the counters and the section. So this element was not added to the DOM. This single element, this fragment element, was returned from app with its children, but only its children were added to the DOM. And that's great, because that means I can properly format what's returning from my function component without increasing the size of the DOM tree unnecessarily. So if you're about to use a div, don't use a fragment unless you really do, for some reason, want to have that root element, like a section or an article or a UL or a paragraph or something else. It's totally fine to have these elements, but stop if you aren't thinking about why they're there. In fact, I can now go on and make these fragments if I choose. Everything still looks the same. Now inside my main, I have my H1, a section, and then immediately my H2, no wrapper. So I've removed 2 levels from my DOM tree, which means my web page rendering along with my CSS will be faster, and that's a good thing. For my purposes, I'm going to go ahead and leave article, but have the main app just be a fragment. And again, we're not saying there's a right or a wrong, because each case is unique. HTML authoring is as much an art as a science. You're deciding where tags need to be and which ones they should be. But that HTML authoring, that's part of your job as a front-end developer, is supported by React. You can use Fragment when you don't really need that root parent element to be in the DOM coming back from the function component, and otherwise you can make good choices, because even though JSX isn't semantic, this type that's being passed to the React element will be turned into a semantic DOM article element or a semantic DOM paragraph element, etc. So think about the semantics of your HTML. Think about the semantics of your content. Think about the DOM that's being created after React does all of its work. Look at the DOM inside the browser. Don't just focus on your code and your components. Ultimately, you'll improve your performance, your readability, and the future proofing of your application. And the next time you go look at some blog post or some YouTube channel where they're building React components and they're wrapping everything in divs, you should look at that and think, that's wrong. This person is not authoring their HTML. They're not thinking about what the content is, what elements should wrap it, and how to improve performance by minimizing the DOM where possible. Make sense? You are not just going to be a JavaScript developer that deeply understands React. I'd like you to be a JavaScript developer that deeply understands React and authors good semantic HTML. That will make you a well-rounded, big picture kind of developer that builds applications that all of your users can enjoy and that you and your fellow developers find easy to maintain. Now that we understand how we'll define our trees using an expansion to the syntax of the JavaScript programming language, that is JSX, it's time to dive in to what's happening under the hood in regards to these trees themselves in order to get to the point where we actually update the real DOM. It's time to understand a fundamental underlying data structure that underpins everything React does. And understanding this data structure will help us to understand all of the elements that come next in understanding React. This section is fiber and reconciliation. In this section, we dive into some code that we've already been looking at and using, but we'll get a little deeper, and it will be the beginning of our journey into fiber and reconciliation. This is root creation and render. All this time in our code, we've been using two functions from within React, create root and render, as part of determining where our React application should update the DOM and to ask it to start doing so, as well as giving it the function that it should initially call. To begin with, I'm going to make a change. I don't want to say react.createElement anymore. I want to use JSX. So I'll tell React to use my app function as the beginning of the render. Call this function, and I'll use JSX. Thus, it's an app element in JSX. This, of course, will be transpiled into the kind of code we saw before in Babel. Now, let's focus on what create root does and what render does. Let's try to find it inside React source code. And as always, React source code will continue to change. So it may be different than at the time this video was recorded, and that's okay. We're just trying to get the concepts. I encourage you to look at React source code for yourself. Now let's open React DOM, and I'm going to do a search for create root. I'll put a parenthesis to make it easier to find because it's going to be a function being created. Create root parenthesis gets me to this function, create root. It takes a container and some options. It expects that the container is a DOM element. And that's exactly what we're doing. We're using the browser APIs. We're getting a DOM element created by the browser. We're referencing it as a variable, and we're passing that DOM element to create root. We're not passing a React element. We're passing a DOM element. And that's what create root expects. If I scroll down, I can see that it creates a new variable called root, and it creates a container. Let's go into that function. Create container. It takes container info, a tag, and other things. Container info is that container that was passed to create root. So my DOM element is passed along to this create container function. And inside there, I see that it calls yet another function, create fiber root. And my same DOM element is passed into that. Create fiber root creates a new fiber root node. And again, that's passing along for the ride DOM element where I'm asking React to begin updating the DOM. If I go into this function, fiber root node, I see that it's actually a function constructor. It's building an object for me, a fiber root node. And one of the things it has on it is a reference to that piece of the DOM that I'm sending it. If I go back, I can see that there's more code here for creating a host root fiber, etc. So when we see the word container, when we think about host, we think about a DOM element that React is actually pointing to update its contents, its children. Now, what are we getting back from my create root function? Well, let's find the end of the function. And it's returning a new React DOM root, and it's passing this root fiber node that was created inside create container. Remember again, create fiber root ends up creating a fiber root node. And that's what's returned back up this chain of function calls. So I get a fiber root node, and then it's wrapped inside React DOM root, which is a very simple function constructor. I'm creating a new object, a React DOM root object, which inside has this fiber root node attached to it. Interesting. It might be a bit easier if we just output this root that's created by create root. Taking a look, I see it's a React DOM root object, which is no surprise. It has this internal root reference, which was that fiber root node that was generated. Remember, we passed our DOM element along for the ride, and there's the reference. Our DOM element was app, which is a main element. And there it is. Our main element with an ID of app has been passed along for the ride. And there's a fiber node. So now we see that we have this fiber root node, which is just an object with a lot of properties and methods. But what about render? Well, if we go back to the code where React DOM root is created, this object, we can see that the React team is using JavaScript's prototypal inheritance. That is to say, on the prototype of React DOM root, they're adding a render function. That means this render function only exists once, but every React DOM root created from this function will have access to that render method. It's a method shared by all the objects created from this function. So this render method that's available to any React DOM root object, it looks at that internal fiber root node. It makes sure there is one. If there isn't, it says cannot update an unmounted root. So there must be a root that's created that is mounted in order to make any updates. And that makes sense. We have to have actually decided where we're updating the DOM and have the beginning of this process done in order to actually render anything. That is, ultimately update the DOM. We see our container, our DOM element, and eventually it calls update container. We'll get into some of this a little bit later, but it's enough to know that it's passing children and root. Children is what's passed to the render function. So in other words, we're saying I have this root and I'm giving you children. We can already see that we're building some kind of tree. So when I call create root, it gets a reference to the DOM element, but also creates this fiber root node element, which is really just a simple object. And then when I call render, it makes whatever I pass to it the child of that root. In fact, when I look again inside this fiber root node, I can see current and then child, and child is my app function, the app function object. To be more exact, that's the type of element for this fiber node. This is feeling an awful lot like the React elements, isn't it? It's saying this node, called a fiber node, is of type the app function object. So the app function object is now part of a tree. But strangely enough, it's a different tree than the React element tree. It's a different set of objects. We need to understand this in more detail, and we need to understand why we're seeing yet another tree in our examination of React's code. Let's move on. It's time for a conceptual aside. In this conceptual aside, we'll talk about trees and linked lists. Big word alert. A linked list. A linked list is a simple data structure that creates a line of connected items. They're linked together. So if I have an item, a node, in the linked list, it points to the next item, and so on and so forth. There's also the idea of a doubly linked list, where items point in reverse as well. In either way, you can traverse the linked list. It's extremely simplistic and also very light on memory because you're not storing a lot of different concepts. You're just storing a node and the links, the arrows between the nodes. And it's very easy to traverse a linked list. You just move from node to the next node. What does that mean in code? Well, let's try building a linked list. We'll do that by going to a popular repository on GitHub of data structures built in JavaScript. I'll base our linked list off that. Let's delete all our code for the moment, and we'll use JavaScript classes to create the objects that we'll need. I'll need an individual item in the linked list. We'll call it a linked list node. When you make one, it takes a value and then a reference to whatever the next node is. That, by default, would be null. That is, there is no next node by default. And inside the node, I'll store the value and that reference. Now I need an object to represent the entire linked list, all of the connected nodes. I'll need two properties, a head and a tail. In this way, I'm referencing the beginning of the linked list, the first item in the linked list, and the last item in the linked list. I already have the code, so I'll just drop in the next method. We're going to append an item to the linked list. That is, add the next one. I'll give it a value. It will create a new node. And if there's no head in this linked list object, meaning it's empty, then both the head and the tail will be this new node, just one node in the list. Otherwise, if there's already a head, then the next item on the current tail will be this new node. In other words, imagine attaching another node on the end, and then that new node becomes the new tail. Remember, we start with the node that's both the head and the tail. Then when we add a new one, the next of the tail becomes the new tail, and so on and so forth every time we add a new node. Now I just need something to help me view my linked list. I'll create a print method, and it will loop over the linked list, outputting the value on the current node, which starts as the head, and then moves along to the next node, looping back again, going from node to node to node, following that next property, until next is null, which will eventually happen when it hits the tail, and that will be the end of it. Now we need to build these objects to make the linked list. Here I'm making a new linked list object, and I'm just calling append with my first name, my last name, and the name of this course. Then I'll call the print method. When I run this, I don't get anything anymore because I'm not running React, but there's my 3 items inside my linked list. We find linked lists inside of React's source code, and I wanted to make sure you understand what they are. In fact, you've already been seeing them before as part of how the trees are structured. Let's take a look again as we keep looking at fiber. In this lecture, we keep talking about fiber nodes and fiber trees. That's right, there's a third tree. We've already been talking about the DOM tree. These are sets of complex objects used by the browser to show us what we see or otherwise interact with on web pages and web applications. We've seen that via JSX, we can define a React element tree. These are simple objects used by React's code, which will call our various functions that make up our components and ultimately generate this tree of objects that can be used to express what we want the DOM to look like. And as it turns out, there's one more very important tree within React. It's the fiber tree. These are sets of simple objects known as fiber nodes that are used by React's code to both store information and determine what work needs to be done. And by work, we mean the work of updating the DOM. And there's an important distinction between the React element tree and the fiber tree. The React element tree is disposed of and keeps being re-rendered, recalling our functions, returning those React elements. The fiber tree, on the other hand, sticks around. As we're clicking around in our application, the fiber tree is not destroyed. It's not recreated. It's updated. And that means it can be used to store information, what we call state, which we'll talk about a lot in upcoming lectures. And because that fiber tree sticks around, it can be used as a middleman between the React element tree and the DOM tree, so that we can figure out what changes need to be made to the DOM tree and the best way to make them before that expensive work of updating the DOM tree is done. And one more thing, the way I drew these trees is a little bit different than you may be used to seeing tree data structures drawn. If you look at this, you can kind of see multiple linked lists. The section to UL to LI is a linked list, and the LI to LI to LI is a linked list. So the line of nodes that form children to grandchildren, etc. is a linked list, and the line of nodes that connect siblings is a linked list. That means the tree is very lightweight and very quick to traverse for the computer. That is, your device, as React is moving through the tree, it's simply traversing linked lists. Now in the future, that could change. But the point being that when you see there's 3 trees involved in React, it may feel like that's a lot. But do understand that the people that make React are doing their very best to keep this architecture as lightweight as possible. And we'll see more on how they do that in just a little bit. For now, understand that we have this fiber tree, a tree of fiber nodes, this fiber architecture that's designed to store information, determine what work needs to be done, and keeps a tree around for us as we interact with our application. If I go back to our React app and I look again at this render function, and remember I passed now the JSX version of app, and I did the same on the re-render, we know now that it's building this fiber tree. And the fiber tree is in essence, a copy of the React element tree from a structural perspective at a particular point in time. In fact, I can even look around React source code and find methods like create fiber from element. In other words, create a fiber node from a React element. These trees are designed to work together. And if I go back to the render method that we've been calling in our app, at the bottom of that function, it's ultimately calling something called update container. Notice that it's not replacing the container or recreating the entire fiber tree, but it's generating an update. That's important, and we'll see that later. But again, it's that idea that the fiber tree sticks around and then is being updated and is causing updates. When we run this and we look at our console.log of our root, we can also dig into the fiber root node and see that if we look at the fiber node itself, there is both a child, which is that single linked list to a single node, and there's also a sibling, which in this case is null because there's no sibling. If I go to the child, I find its app. If I go to that child, the next item in the linked list, the child of app is H1, and that has no children, but it does have a sibling. The sibling is a section, and that matches what we see in the DOM. H1 doesn't have any children other than this text itself, but it does have a sibling, section. So we can see the tree structure being defined essentially by multiple linked lists. And we can imagine React traversing this tree by moving from node to node along these linked lists, each node being a fiber node. What's inside then of each of these fiber nodes, what's attached to each of these fiber nodes, will define how we understand much of the features we'll see that React has going forward, because they're built on top of the fiber tree. One more thing. If I console.dir, which will work in Google Chrome to force whatever I put in here to be outputted as a formatted object, if I output the DOM node that is my app, that is my main element that I'm mounting my React application to, I can see my DOM element, and React has added to my DOM element a reference to these fiber nodes. Remember, we saw that earlier, and that's what's going on. The DOM has a reference to the fiber nodes, and the fiber nodes have references to the DOM. Let's move on. It's time for a conceptual aside. In this conceptual aside, we'll discuss tree reconciliation and the tree edit distance problem. And right away, big word alert. Reconciliation. The idea of reconciliation in our case is comparing two items to find the differences between them. So when we say tree reconciliation, we're comparing two trees, that is, the contents of two tree data structures, or the portions of trees, the equivalent portions of trees, and finding the steps needed to make them match, to make one turn into the other one. Figuring out what those steps are, the steps to change one tree to make it match another tree, and then minimizing those steps is sometimes called the tree edit distance problem. Big word alert. The tree edit distance problem. What is the algorithm to find the smallest number of steps to change one tree to match another? So there are two things to break down here. When we say the distance between two trees, we're trying to figure out what's the minimum number of steps to turn one into the other. The number of steps is the distance. And finding those number of steps is important because if we can minimize the number of steps, we can minimize the amount of work that we're doing on the tree. So for example, the tree on the left and the tree on the right. What's the minimum number of steps to turn the tree on the left into the tree on the right? In this case, we might say, well, adding one li. But what if there was more complexity below the LIs, more children? Maybe the minimum number of steps would be one step, but that step would be removing the UL and completely replacing it. It really depends. This is what we call in computer science a non-trivial problem. Not only do we want to find the minimum number of steps, but the methodology that we use to find the minimum number also needs to be efficient. It needs to be an efficient algorithm. Big word alert. An algorithm. A step-by-step procedure for solving a problem or computing something. So there could be various ways, various approaches to compare two trees and try to find what's different about them, and then find what we need to do to make one turn into the other one and minimize that effort. The algorithm itself that searches those two trees, compares them, etc., that also needs to be efficient. We're trying to save how much work is being done by the computer, which would translate to time, slow applications, applications that take up a lot of the computer's processing power or a device's battery power. These are problems that React is dealing with. Inside React, then, we have an algorithm for carrying out tree reconciliation by solving the tree edit distance problem. Now, we don't need to dive into the algorithm itself. That's beyond what we really need to know to understand how to use React and to understand how to debug it. But the point being that you can understand what we're talking about when you read and hear things about React tree reconciliation. Now you know, and we can appreciate that React is doing this work for us. We are only defining our trees with JSX. React is doing the rest. We've already seen that inside React, there's another tree, a third tree, the fiber tree. But how does it work? This is work in progress nodes. When we think about the fiber tree, it's in comparison to the React element tree that we've been talking about all along. How do they relate? Well, the fiber tree essentially matches the current state of the DOM, whereas the React element tree is us telling React how we want the DOM to appear. To illustrate, if we think of the React element tree like a blueprint, where we're deciding how we might want to make changes to a house that already exists, then the fiber tree is like a small model of our house, where we can look at the blueprints, test out how to make the changes in the best, most efficient way possible before we actually start working on the real house, which would be the DOM. Working on the small model home is less expensive and could have other benefits. So what happens when we tell React via JSX, via the React element tree, that we want the DOM to look different than it currently appears? Keep an eye on the 3 LIs in the React element tree. Let's suppose the React element tree re-renders, and now it only has 2 LIs instead of 3. Now we want to update the DOM to match. This might be a situation, for example, where you remove one item from a shopping cart. You had 3, and now you have 2. The piece or pieces of the React element tree that have changed are the pieces that we're worried about, the branches of the tree, so to speak, that need to be updated. And so React takes those pieces and attaches them as a kind of sideways piece of the tree called the work in progress branch. While the current branch matches what's currently in the DOM, the work in progress branch matches the latest React element tree. The reason for this is instead of creating 2 fiber trees, we can jump back and forth between these branches when doing comparisons and traversing the tree in a more efficient way. That's how React is working to do this work as efficiently as possible. And speaking of efficiency, I should say that right now we're a little bit oversimplifying things. It would be inefficient to call every element in your React element tree, to call every function every time. We have to the first time. But for subsequent changes, it would make sense to only call the functions that represent areas of the tree that may have actually changed. If nothing's changed, then why call the function again? The fiber tree actually helps us do that, so that only those pieces that may have changed are what's analyzed. However, we can't quite get into that yet because it requires getting into an understanding of something called state, but we will get into that later. For now, for your mental model, you can think of pieces of the React element tree re-rendering, and essentially we have a re-rendered full tree at that point, only some of the pieces are what changed. The fiber tree is what's actually handling those changes, calling those functions, dealing with what might have changed after the initial render into the DOM. Now, if we wanted to update the fiber tree so that it looks correctly like the React element tree that we've given it, there's an easy way to do that. Note the connection between section and the UL. I can simply move that connection to the new UL, the work in progress UL, and see this alternate arrow where it points between the current and work in progress versions of that branch. I can just flip them around. So now, after the DOM is updated, the right-hand side would be the current, and the left-hand side would be the work in progress. And really, I don't have to think too much about the work in progress anymore. Now it's just ready for the next change, the next time the React element tree re-renders. So we can imagine with every change to the fiber tree, connections from nodes moving back and forth between the current and the work in progress. Let's prove that's what's really happening by looking under the hood of React source code. I'll go inside the react-dom file and find a function called createWorkInProgress. That's where it is currently at the time of the recording of this video. And again, it could change. But what we're looking for is this idea that there's a current branch of the tree and an alternate branch. That's called work in progress. If we go down this tree, we can see that work in progress has plenty of different properties on it, and we'll see how some of these work later. And again, it could have sibling or child references for the linked lists that build the fiber tree. Let's go all the way to the bottom, and I'll log to the console this work in progress fiber, which really is a node of the tree that's attached as an alternate to a different node marked as current that matches the DOM, and this work in progress is ready to be used for updating the DOM. Now I'm going to run my re-render app. I have counter 1, and when I click re-render, I'll get counter 2. There's all of my appending and removing of the actual DOM. But notice that various fiber nodes were outputted that are work in progress branches. If I look at this last fiber node for section, which is the area where things have actually changed inside this section, I can see there's a child along that linked list whose type is counter 2. So at this point, we have the updated version of the fiber tree. It's the work in progress. The new branch of the tree should use counter 2 instead of counter 1. Remember, that's what we did in our code. We have a counter and a counter 2, and each of these components will be called one or the other on the initial load 1 and on the re-render 2. So counter 2 is the work in progress. We need to update the DOM to match what it looks like when counter 2 is the child of section. And we can see the rest of it down the linked list. There's the child in an article. There's an H2. H2 has a child that says counter, and it has a sibling with the value of 2. Counter 2. So that's the work in progress. And what about the current? Well, we can go across the tree from section using alternate, which points back and forth between the two, current and work in progress. What should we expect to see in alternate? Well, I see that I have a section, but no child. And this is because React is being as efficient as possible. We already know what this area of the tree looks like. We can actually find those children here inside a method called memWisedProps. And we'll talk about this later as well. But inside this children property that React provides, I can find the fact that we're using the original counter component, not counter2. And the name being passed to it is 1. In other words, React already knows how to render this because it's done it before. Point being that regardless of how this is implemented, and it could change over time, the core idea is that on one side of the tree, you have the original that matched the DOM. And on the other side of the tree, you have the work in progress, what the DOM should look like. It should have counter 2 instead of counter 1, etc. Later on then, React will then do the work of actually updating the DOM to match the work in progress, after which the work in progress becomes the current. But what about the step in between this work in progress area and the actual updates of the DOM? That's next. We understand that the fiber tree represents a combination of what's currently in the DOM tree and how we want the DOM tree to look as represented by our React element tree. So how does React determine how to solve that tree edit distance problem from the React element tree to the DOM tree using the fiber tree? This is reconciliation and work. We've already seen that we have the fiber tree, which contains pieces of the re-rendered React element tree, and that there's two sides to this branch connected by an alternate arrow, so to speak, the current and the work in progress. We've used the idea of a blueprint, which is the React element tree, a tiny model of our home, which is the fiber tree, and our real house, of course, would be the DOM. Now the question becomes, as we're looking at the blueprint and looking at our tiny home, we're figuring out what are the changes, what are the order, the steps that I should take in order to make our tiny home match the blueprints. And once we figure that out, we know exactly what to do on our real home. So what is the process? Well, with the fiber tree, we have everything we need. We have what the DOM looks like and what we want the DOM to look like with the current and the work in progress sides of the branch. What React then implements is a reconciliation algorithm. React looks at the fiber tree and takes the current branches and the work in progress branches, which effectively act like two different trees that are merged together, and by comparing them, figures out the steps to take on the real tree, the DOM tree. For example, it might look at this current, which has 3 LIs, and the work in progress, which has 2 LIs, and decide that we just need to delete 1 LI. Or maybe in another case, there was a lot more underneath the LIs that's more complex, and so decides the simplest, the quickest, the most efficient step would simply be to delete the entire UL and replace it with a new one. And we can actually see the decisions that React has made under the hood. Let's go back to that fiber node we saw, the work in progress fiber node. If I open it up again, I'll see that there's a property called deletions. You see, React decided to delete something. What did it delete? Well, if we open it up, it's a fiber node, and it's the counter component. That's a node of the tree, and the counter component itself returns some JSX. But the point being that React marks the tree for what needs to happen. In fact, there's another property called flags. This is set to the number 16. Let's go back to React-DOM. I can find an area there where various flags are defined. They're defined numerically. No flags is 0, for example. And if I look at child deletion, that's set to 16. So the flags property is set to child deletion, meaning that one of section's children should be deleted. And the one that should be deleted is counter. That makes sense in this code because counter is set to counter 1 and it's the direct child of section on the initial render of this app. When I click re-render, it's going to change from counter 1 to counter 2, this function component. So it says delete this counter function component, and then it will add the results of this new counter 2 function component to figure out what the DOM should look like. And there you have it. This idea that React has done this work, this reconciliation algorithm, and has figured out the best steps. Then it takes those steps on the real tree. Remember, if I look at my console, what's the next thing that it does when it actually takes the steps on the tree? It removes a child. It removes the DOM elements that were returned from where? That were returned from counter, because that's what was deleted. Then it appends the children that were generated by looking at the JSX returned from counter 2. So React made a plan using the fiber tree and carried out the plan in the real DOM tree. And we saw the effects then appear on our screen. Pretty neat, right? We don't need to know what's inside the reconciliation algorithm because that could change over time and doesn't really do anything for us as far as understanding how to use React. But the fiber tree is the foundation of a great deal of what we're going to talk about as we go forward. So understanding this basic step is just the beginning. Because the fiber tree isn't destroyed, because it sticks around, it's used for a lot of other important things, fundamentally important things within React. But at its heart, this is what React is doing for us. It's letting us express how we want the DOM to look, and using this intermediate tree called fiber, it reconciles the DOM tree and the React element tree. And we don't have to do any of it. Let's move on. We've seen now that React has work to do. In this section, we'll talk a bit about how it organizes that work. And again, this will be built upon later in the course to help us understand how to use React well. This section is execution context. It's time for a conceptual aside. In this conceptual aside, we talk a bit about something that goes on inside the JavaScript engine, which is then embedded in some other system, like the browser or Node.js. This is execution context and the event loop. This is a topic we've talked about a lot in some of my other courses, and you can find information for free on this on my YouTube channel. So we're just going to get an overview of what we're talking about. When you run JavaScript code inside the engine, and that engine is embedded inside another system like your web browser or Node.js, code is run within what are called execution contexts that sit on the execution stack. For example, if you're running global code and then it calls a function, the function immediately starts to run, and that function sits on top of the global function in the stack. And calling that function ends up creating what's called an execution context, which contains all of the variables that might be used within that function, everything that's needed for the engine to execute the function. But there's other things going on because JavaScript is embedded inside other systems, like in the browser. For example, there's a queue of events, things that might happen that are initiated by the user or initiated by the coder writing the program. This sits inside then of the engine, which is embedded inside of the browser, Node.js, etc. And the engine has access to this queue, but so does the other code outside of the JavaScript engine. So let's say we set a timer with set timeout, and we pass a handle or a function that should run when set timeout ends. The code keeps running. Maybe function 1 is running. And while function 1 is running, the timer ends. But at that moment, nothing actually happens because the timer was counting down outside of the JavaScript engine. The event, which could be a click event, for example, a mouse over event, an animation from CSS, or a timer ending from set timeout, ends up in the queue as saying this happened. But when will JavaScript then react to what's happening? Well, after it's finished running other code. Then it checks the queue and might call the callback handler. This idea in general, that JavaScript is running code line by line, and when the engine becomes available again, might then run other code based on other events happening outside of the engine itself, is fundamental to understanding how things work within JavaScript. This loop of things that happen, that is events, and JavaScript reacting to them, is called the event loop. And there's more detail here that we're not going to get into right now, but suffice it to say, React recognizes that running its code is not the only thing that may be happening in the browser. You may be watching a CSS animation. You may be clicking on the web page. And so React doesn't want to interrupt what else you may be doing or experiencing. So because it has this work that it needs to accomplish, all of which are called in functions, which end up as execution context within the JavaScript engine, it tries to make sure that those things happen at appropriate times, at times when other more important things are not happening in the browser. And React keeps track of those things with a few ideas, which include some borrowed terminology. React tries to be efficient, so it wants to organize the work that it does. This is Fiber and custom execution contexts. Now, for starters, when we say custom, we mean that React has borrowed the term execution context and has created something within its own JavaScript code that uses that term. But it's not the same as the execution context that exists within the JavaScript engine. However, what it does share is a similarity of purpose. An execution context within React's code is a way for it to know where it is in the code, so it can decide if it wants to do work and what work to do at that particular moment. We can find references to these types of execution contexts within React's source code. There's no context, a batched context, a render context, and a commit context. And again, these may change over time. But the idea is that at various points in time during React's work, this context will be changed. In fact, below it starts the variable execution context, which starts with no context. For example, I'll find a point inside a function called commit root impl, and there's a little comment here, opportunity to paint. In other words, in this section of the code, React is saying, wait a moment, I'm going to stop doing work. I'm going to stop running my own code and let the browser decide what needs to happen next. For example, if the browser is painting an animation, moving something across the screen, that animation would freeze if React did all of its work at once if there was a lot of work to do. So you might see stuttering, jittery animation. By essentially React pausing, that is stopping what it's doing and saying, I'm going to put in the queue an event that says, keep going once you're done doing whatever else you need to do, browser. Then the browser can go off and do its own work, and then it will find React sitting in the queue, an event that React put in the queue, and it will continue running what React wants it to do. As React moves through these pauses and continues, the execution context, React's execution context, may change. So, for example, if I log to the console, I can see that in my example app, the execution context is a 4. And back in the code, I can see that 4 was the commit context when React is committing work. And we'll talk about that a little bit more in just a bit. Suffice it to say, we can imagine React running some code in a particular execution context, saying, well, this is the code that should be running, essentially saying, browser, please use one of your execution contexts to run this code right now, the thing that's created inside the browser when a function runs. And when that's complete, React may have said, well, when the next opportunity is available for the browser, I'm going to stop my code right now. I'm not going to ask it to continue. Instead, I'll use features similar to set timeout. Say to the browser, when you're ready, here's some more code to run. That's why with React Fiber, if you look it up on the internet, you might see examples where it shows previous versions of React and the newer version of React and shows how While React is doing work, things like animations and painting things to the screen are much smoother and faster. That's because React, thanks to the fiber tree, can build up work to do, such as calling different component functions and updating the DOM, and split that work out. Pause and resume, essentially, by using the methodologies that the browser and the JavaScript engine naturally provide. So have that in your head. What's happening in the fiber tree is not all happening at once. In order for React to do all the work it needs to do, it needs to keep trying. It needs to stop, pause, allow the browser to continue, but then continue its work. This is units of work and the work loop. I'm going to show you a function inside the React DOM code. And as always, this may be different by the time you look at React source code, but the fundamental concepts will be the same, likely a different line number inside the code. This function, work loop sync. Notice that it's just a while loop while there is a work in progress, and then it performs what's called a unit of work. So what is a unit of work? If I go into the function, I can see that we're passing a unit of work to the function. So what are we passing to the function? We're passing a fiber, a particular node which may have children and siblings, so a piece of the fiber tree. Remember, we said that maybe not everything will change, so maybe not everything needs work. We're looking at particular pieces of the fiber tree at a time. Now, where is this function called? I'll go to a reference, and I find it here inside this essentially infinite while loop, a do while that just stays true, but it breaks as soon as the work loop function ends. And the work loop function ends as soon as there's no more work in progresses that need to be acted upon. So at this point, when we're thinking about the fiber tree, we're seeing how it actually solves multiple problems at the same time. And there's more to come. We've already seen that it matches the DOM and the React element tree changes. In reality, it contains references to pieces of the React element tree that it can recall, functions that it knows to call again when something changes. So far in these visuals, I've just been showing React elements that match up to HTML elements, but really, a React tree is generally made up of components. So the fiber tree might have a list function component, which then returns React elements that match up to basic DOM elements. And we can think about these components and what they're returning as units of work. If something changes, if work needs to be done, then that portion of the tree is what needs to be worked on. It's a unit of work. React is looping over and over again as long as there exists work in progress that needs to be done. However, that loop can be interrupted, as we saw before, by taking advantage of the event loop that exists inside the browser and the JavaScript engine. And inside that work loop, React is doing everything that it needs to do to keep our application running in reality in the DOM. It's time for a conceptual aside. Let's talk for a moment about equality in JavaScript. Anyone who's worked with JavaScript for any period of time knows that equality can be a tricky concept. And when we say equality, we mean checking that two things are equal to each other. But we've already said that React is doing work if something changed. And when we say if something changed, that usually means comparing if two things are equal, what came before and what came later. There are a few different ways to compare if two things are equal in JavaScript. For example, there's the comparison operator to check for equality, and there's the strict equals comparison operator. One will try to convert the two things to be the same kind of thing, and the other one won't. So here, these first two console logs, we end up with true and then false. The one number and the one string were converted into the same type of thing, and in this case they weren't, so they're not the same. In the next case, I wrote two equivalent objects. They have the same property and value. And then I set a third variable equal to this original object. In one case, they look the same. In this let C equal A case, they both point to the same location in memory. So they really are the same in that sense. That's why when I log if A equals B versus if A equals C, I get false, then true. A does not equal B, but C equals A, because the comparison operator in this case, in the case of these objects, is comparing if it's actually the same location in memory, not what the objects look like. A equals B, just the not strict version, also says false. There's another method of comparison that you may not be as familiar with. It's called object.is. We pass it two things, two objects, and we pass it two things to see if they're equal. It behaves very similarly to the strict equals, the triple equal sign, but it behaves a bit differently under certain circumstances, like if something is marked as not a number NaN. When I compare A and B and A and C, I get the same results as the triple equals. False, and then true. A does not equal B, but A does equal C because they're the same memory location. This makes sense, but sometimes we would want A to equal B. For example, if I'm deciding whether or not to call a function over again, and I say, well, the first time I passed it A, and I got a result. The next time I pass it B, the function would return the same result because the object looks the same. It would process the object and get the same result most likely. And so I would want to say that A equals B in that case. I would want to be able to say, well, if you pass B, and I've already passed A before, for the purposes of whether or not I need to call the function again, A equals B. I already know what the function will return for B because it looks just like A and we've used A before. That is another layer of complexity in the idea of equality. Let's move on. So we have a clear mental model. Let's talk about what happens a bit more inside the work loop. This is beginning, completing, bailing out, and pausing work. When we look inside React source code, we see that we have this work loop where it's working through any work in progress fibers. If I go into the perform unit of work function here, I can see that we're passing it my work in progress. The current is the alternate of the work in progress. That makes sense. And then we set the current to the work in progress. Remember how we moved that arrow from section to the current UL to the work in progress UL and made that the current? And then it begins the work where we can compare the current fiber and the work in progress fiber. And this will be a function that will do various things inside the React source code. And as we go down, you can already see, for example, the idea of equality. It's checking to see if old props is equal to new props. That is to say, on the current fiber, if the memwise props equal the pending props on the work in progress fiber. Big word alert. Memwisation, or to memwise something. That's to store the result of a computation, so you don't have to repeat the computation itself. For example, if I had a function and I pass it 1, 2, 3, and it takes a really long time to figure out the answer, and then I get a result back, I could store the result and the values that I passed to the function. So if I try to call the function again with the same values, 1, 2, 3, instead of calling the function, I'll just grab my memwised value. That is, I already know what the function will return if I give it particular values, so why run the expensive function again? Instead, I can just store it. And we keep seeing that word. For example, if I go down into the fiber and I'll go over to the section element, it has memwised props. Memwised props meaning the values that were passed to the function. In this case, children that contained the counter function that was called. So inside the fiber, it stores the values that were passed to functions when they were called. This helps it decide if it needs to call the function again. And so it compares. If they're not equal, then we need to do some work. Of course, it's more complex than that. As we said, equality can get complicated. If I scroll down, for example, I check the work in progress flags. Remember, it's saying what kind of work is necessary. And at this point, if I see that there's no work necessary, we can do what's called bailing out, meaning you just stop. I don't need to do anything more because I compared the two trees and I know I don't need to do any work on them. And so it will attempt an early bailout. This is React attempting to be efficient. If I know there's no work to do, then don't run any more code about the work. Now, going back to inside my perform unit of work function, I've seen we can begin, we can bail out if there's nothing to do, and we complete the unit of work. Inside the React source code, you'll sometimes see what's referred to as flushed state of something, meaning that everything really has been processed. So we can see once again that it's going to look at flags on the actual fiber, which is also referred to as a unit of work or completed work or beginning work, and finishing out whatever's left to do, and marking everything as complete, doing all the things that are necessary at the end of this process. Now, we won't get into all of that, but understand that because React organizes work well, it has places for other things to happen. Something that might happen before the work begins, during the work, or when it's completed. And we'll see some of those things as time goes on. We also know that inside the work itself, it could choose to not execute the work until the browser is done doing other things. React has set up a structure, an approach to the code that maximizes its efficiency to help the app appear fast in the browser. And it helps React add other features that we'll see soon. Let's try something real quick. Inside our perform unit of work, let's put some console logs. I'll say that we're performing work. Inside the begin work function, I'll say that we're beginning work. And inside the complete unit of work function, I'll say that we're completing work. And I'll log whatever that unit of work was that was completed. Again, that will be a fiber. When I run this, and I have other things logged, but here we go. Performing work, beginning work, and then it bails out. Performing, beginning, and then it did find some work to do. And the unit of work is a fiber node. Over and over again, we see it. And then eventually it does find more work to complete, another fiber node, etc., etc. When I click re-render, it does the same. And every time we think about work, what we're actually seeing in the console are fiber nodes. React moving through the fiber tree, figuring out what actually needs to be done, and when it finds something that needs to be done, doing the work using the nodes of the fiber tree. Let's move on. There's one last thing to mention when we're talking about how React organizes its work. This is lanes and priority. When we look again inside the perform unit of work function, and we see we're beginning work, it passes something called lanes. What are those? Well, if we look inside a fiber node, we see that it's a property on the object, lanes. And if we look around the source code in React-DOM, I find various lane types. There's no lane, which is a 0, and then there's a bunch of other lanes. What are lanes? Well, lanes are how React prioritizes the work. If a fiber node represents a piece of work and it has a lane, then we could order the nodes in terms of the lanes. We could say, well, I want to do this first, and I want to do this later. And that's actually what React does. If I scroll down, I find a function called getHighestPriorityLanes. And then I see in order of priority. The last, for example, is off-screen lane. If something is off-screen, it's the lowest priority. I can look for examples of usage to try to understand it. For example, inside the complete work function, it's looking at how long it's taking between the time that it began the work and at a particular moment in time. And then based on what kind of lane it is, it may decide to stop trying for the time being. React is trying to make sure that your application renders to the user as quickly as possible. There isn't really a need for you to understand each of the lanes and work with them. That's something that happens internally to React. But if you're going to dig around inside the React source code, it's good to understand all the pieces that have to do with React organizing this work. And this foundation we will then be able to build upon to understand the things that we do use as developers who are using React. In this lecture, we'll go back briefly and take another look at something that we've already seen, but this time with the fiber tree in mind. This is the React DOM and rendering. In this lecture, we'll take another look at committing work and the renderer, this time with our knowledge of the fiber tree. I've already logged to the console various points in React DOM where it updates the DOM, where it does this work. But now if we look at these functions, for example, commit mutation effects on fiber, I see that it's passing a unit of work, finished work, meaning that the fiber tree now knows what needs to be done to perform reconciliation. And so when the update is committed, when the work is committed, it's committed to the DOM. For example, if I go to commit reconciliation effects, and the comment here says placement effects, insertions, reorders, etc., they're scheduled on the fiber to happen at some point. For example, I can go to commit placement, and a unit of work, finished work, a fiber node is being passed to this function. From there, I can see that it's doing a couple of things. It's looking at recursing through the fiber tree to find all of the children of the node I just passed to it so that it does the work down the tree. And it's also passing both the node itself of the fiber tree as well as the DOM reference that the fiber node has. If I go to insert or append placement node, I can see that the DOM node is passed to append child. That's the parent instance. And then the DOM child is appended, as we've seen before. And elsewhere, the linked list for children and siblings are being used to move around the fiber tree. So we can imagine that this work is done. We know what flags are there on each fiber node, what work needs to be done. And then it moves around the fiber tree, updating the DOM nodes when needed, when appropriate. So when you look through this code, understand that we're dealing with two different trees. The fiber tree, the nodes that we're recursing around, and the DOM nodes, which we have references to and React is updating as needed. This is all work being done by what React calls the renderer. But it's overly simplistic to think of it as just rendering a tree. It's really rendering three trees. We know we have a React element tree from our JSX. We have a fiber tree generated from that React element tree, which then can call again different portions of our React element tree. And we have the DOM tree that's being updated and what we interact with as users. All of this is happening inside React. So when you hear or think of React committing work, that's what this is. It's actually doing the work that is calculated to be necessary. Our understanding of the fiber tree and the reconciliation process helps us to understand another important aspect of React. This is mounting, updating, and unmounting. In React, you may hear three terms that will now make more sense now that we understand some of the internal workings of React itself. First, there's the idea of mounting a component. We know in the fiber tree, we have the component as a reference inside a fiber node, and that component itself will return React element objects, which will also be converted into fiber nodes. When the reconciliation process is completed and the work is committed, that act of adding the DOM nodes to the real DOM tree based on a particular component is known as mounting the component. You can think of it like when you mount a picture on the wall or mount something to a tree. You're hanging it, you're placing it, attaching it. And so the DOM nodes have been attached based on what the component said the DOM tree should look like. Thus, the component has now been mounted. Later, the fiber tree may get a work in progress update and update the DOM nodes accordingly. That's then updating. The component has already been mounted, and so now the component is updating. Later on, the component may be removed from the fiber tree. Maybe an if statement that says only show this component under a certain circumstance. The corresponding DOM nodes are removed, and thus the component is unmounted. That's the terminology that React uses. However, note that it may be that a component is unmounted and replaced with another component that results in very similar DOM structures. Unmounting the component doesn't necessarily mean that the DOM nodes created from the component that was unmounted will also always be destroyed. It depends on what the fiber tree ends up looking like. If another component, for example, returns some very similar DOM elements, the reconciliation algorithm is going to take care of how to actually update the DOM. Just as an example, inside our React DOM code, and again, this may change, but at the time of the recording of this video, there's a function called getNearestMounted fiber. That means that the fiber node has been run and the DOM elements that the fiber node would indicate should be created have been created and added to the real DOM. So if I give it a fiber node, it will say find the nearest mounted fiber. If I go down, we'll see that it's actually going through using a return variable, which is basically moving the opposite direction of the linked list, and ultimately working to try to find a node that's already been placed. For example, if we hit a node that's attached to the host root, remember the host is the actual DOM elements, then we know that that particular node is mounted. Host root, if I go to the definition, is a value of 3. Going back to our app where I've already logged fiber nodes, I see that the very first fiber node I come across has a tag of 3, a host root. That makes sense, that's where we're starting. And I can see that it's the main DOM element. That's our host. So the fact that the fiber node has a reference to a real DOM element that's sitting in the DOM means that component is mounted to the tree. As we think about then our components in the fiber tree, what's mounted, that is the DOM elements are there, created in the real DOM, what's updating, when DOM elements are being updated after they've already been added, and unmounting, when DOM elements are removed as needed, when the component is removed from the fiber tree, are all points in time in what we might call React's life cycle, the things that happen, the things that React does over time. Having an understanding of that life cycle will help us understand the timing of React when it comes to other features where React allows us to carry out our own code at certain points in the life cycle. So keep this idea of mounting, updating, and unmounting in mind, and let's move on. So far, we've only really looked at React providing information to us, the user, via updating the DOM. But if we ever wanted to build a real application, we need to accept user input. And another way of saying that is we need to deal with events. In this section, we'll see how React does just that. In this lecture, we talk about how the browser enables us to deal with user input, with the user doing something. This is DOM events. Let's imagine we have a DOM structure like this, an unordered list with the list item, which then has two links and a button that are siblings. I want some JavaScript code to run whenever I click the button. Clicking is an event. It's a thing that happens. And so the browser provides a way to what it calls listen for an event. When the event occurs and the JavaScript engine is ready to run some more code, I can set up some code, tell the JavaScript engine, run this code when this event happens. In practice, we say that the event is a click event. The target is the button, meaning what is the thing that will be acted upon, the target. And the handler, the code that will run, the function that will be executed when the event happens on the target, in this case is usually called an on-click event handler. These three concepts aren't React concepts. They're general concepts, and they're how the browser implements dealing with user interaction in the DOM, as well as other interactions that you can program with your code, for example, a timeout. But in the case of the DOM itself, we're looking at events on particular targets. And we can have multiple listeners on multiple targets within the DOM. For example, I could listen for a click on either of these A elements, either of these links. And there's something very interesting that the browser does when an event occurs on an element. For example, if I clicked on any of these siblings, A, or button, not only would the browser register that we need to run any handling code for clicks on those elements, it would also register the fact that the LI was clicked on. The LI is the parent. And so the button and the two links inside the LI, if one of those are clicked, that also means the parent was clicked. This idea is called event bubbling. Big word alert. Event bubbling. That means handling the event on the innermost element and then moving up through the ancestors to handle the same event. So in what order do the click handlers get called? They'll get called at the lowest level of the DOM and move their way up through parent, grandparent, etc. For example, if I clicked on the A and there was a listener, then that listening function would be executed. And then if there was also a listener on the parent, that function would be executed because the event is bubbling up. The A was clicked on, and that means the LI was clicked on. And by the way, that means the UL was clicked on. Make sense? And by the way, there's a reverse version of this idea. It's called event capturing. Big word alert. With event capturing, we handle the event on the outermost element and move down through the descendants to handle the same event. So in that case, it would be the UL that would handle the click first, then the LI, then the A. We mention event capturing because the browser actually does it. First, the browser goes down the tree with capturing, and once it reaches the target, it goes back up the tree via bubbling. However, capturing is rarely used, and the things we're talking about going forward mostly have to do with bubbling, going from the lowest point in the target up. You can instruct the browser to run code during capturing, which happens first, but the built-in ways via the browser to run code against events are dealing with bubbling, which happens after the target is reached, down to the DOM, and then bubbles back up. Since event capturing is rarely used, we're not going to talk about it or show it, but just be aware that it exists. Whether we're dealing with event bubbling or event capturing, we're dealing with the overarching idea of event propagation. Big word alert. Propagation. To propagate something is to transmit it in a particular direction through a medium, like propagating something through water or through air. In our case, we're talking about propagating something through the DOM tree. So event propagation, big word alert, means event bubbling and event capturing. Just the idea of the event, the click the mouse over whatever the event is, moving through the tree, through the relevant DOM nodes that should know about the event. And there's one more important concept, the idea of how many listeners do we actually need to register if we have these events going up or down the tree. We can do something called event delegation. Big word alert. Event delegation. That's assigning an event handler to an ancestor node in the tree. And what we mean by that is think about each of these listeners as taking up some memory space in your device or the computer inside the browser. Lots and lots of listeners can actually be inefficient. So what we could do, especially if we had a very large DOM tree, is place a single listener on some root, some ancestor element, because we know that no matter what happens down below that node in the DOM tree, my root will eventually receive the event. So if I clicked on the A, even though there's no listener and there's no function to run, the DOM is still going to say, hey, LI, you were clicked on, and it will still say, hey, UL, you were clicked on. And if that UL has code, it could have code that deals with which ancestor was clicked on and run different code depending on which ancestor. There's ways to do that. Let's take a quick look. Let's do some event delegation. To do that, I'm going to run some code that has nothing to do with React. It's purely DOM code, just like I did in the first line of our application where I got a hold of the root node, which I ID'd with app. This is now the DOM element. And so thanks to features provided by the browser to the JavaScript engine, note these things don't come along for the ride in JavaScript. They're added to JavaScript by the browser. I have a special function on any particular DOM node called add event listener. And I can say, what's the event that I want to listen for? And they're predefined by the browser itself. And then inside the function, well, let's start by just taking a look at what is passed to the handler by the browser. When I click me, note what happened. I added an event listener to the root of my application, main. And inside of it, going all the way down, is that button. So clicking the button caused the event to propagate up the DOM tree. It went up to article, then section, neither of which had any event listeners, so nothing was run. And when it hit main, I had registered an event listener via my JavaScript code. And so that function ran, and I see what was outputted to the console. It's called a pointer event. And this, again, is an object provided by the browser. There's lots of things here, but one thing I can go all the way down to see is the target. What was the thing that was acted upon at the lowest level of the DOM? It was a button. I can go inside this target object. There's a lot there, and notice all of the possible events that could be handled, like on blur, cancel, change, click, etc. I'll open up the rest and see that there's a tag name, button, the name of the HTML element. I could use that, for example, to figure out what was actually clicked. Because when I'm running the code, all I know about initially is that I clicked on the main element. It's hard to see right now because there is a property here called current target, which is null. It's null because by the time we're reading this in the console, the function's already finished running, the event's been handled, so there is no current target. But if I debug my code, meaning going into the source code within the browser and setting a point to pause the code, and if you're not used to doing this, it's beyond the scope of this course, but definitely something you should be learning how to do. I can pause the code, and we'll take a look at the event object at that point. I'll click, and I can look inside this event object. It's the same event object, but we're still within the execution of the event handler. So now we see that the current target is actually main. But again, what if I wanted to run code only if the button was clicked? I only have one event handler, but thanks to target, the original target, not the current one, I can see that the original target was button, even though the current target is main. So let's put a little bit of code to do some delegation. I've delegated dealing with the event to the main element, to the root element. I want that single root element function to then decide what to do depending on what was clicked. So for here, I'll say, if the target's tag name is a button, I'll just log to the console, clicked button. But if it wasn't, if I click something else inside main, I'll say didn't click button. Let's try it. Click. It said, click the button. And now click anywhere else. Didn't click the button. Click on the header. Didn't click the button, etc. In all of these clicks, I clicked somewhere inside main, so the event handler was run. But in my code, I checked the original target, the lowest level thing in the DOM that was actually acted upon. And then I ran some code specifically to that. So you could imagine if I had multiple buttons, I could check which button was clicked and run different code for it. Instead of having a separate handler attached to each button, I have just one handler where I've delegated work to that handler up the tree, event delegation. Dealing with adding all of these listeners, dealing with delegation yourself could be tedious in a large application. And so React helps us by doing this code that we've been writing here for us. Let's see how. How does React help us to work with events provided by the browser? This is React Event Objects. React's approach to helping us manage events is to use event delegation and then let us specify on individual targets the events we want to handle, while React handles calling the actual event code appropriately. To see that, I'll go into React-DOM and find a function at the time of the recording of this course called listen to all supported events. And it takes the root container element. In our case, that will be main. And as we go down through, we'll see that what it actually does is look at all possible events, all the events that the DOM provides for, and attaches a listener for all of them to the root. In this way, the root element of our application has been delegated to for dealing with anything that happens on any of the elements inside of our root, that is, our entire application. React used to attach this higher up the tree, but now it attaches it to the root element of our application in case we have multiple React applications on a single page. That is, multiple roots on a single page, which is possible. I'm going to go ahead and add a statement called debugger, which will just pause the code for me. And when I look at this, I can see that the root container element is main. And I can also see that it has a list of all the native events, all the events that the DOM handles, like cancel, click, close, copy, drag, and so forth. So React is delegating all of these events. There's the listener in the root for every possible event. I'll remove this debugging statement. Now that we know there's a listener at the root, what is that listener doing? Well, on the actual object where I'm defining what will eventually be created as a DOM element, where I'm defining my React element, React provides methods to handle the events, and it matches up to what the DOM does. However, note that different browsers do have some small quirks between them, differences in how events can be dealt with or what certain things are called. So React is generalizing it, wrapping it all up so that no matter what browser we're using, our code will work. For example, I'll say onClick equals, and then curly braces because I'm dealing with some JavaScript code here, a JavaScript function that I want to call. Let's imagine I call my function clickHandler. I need to define it. I could define it inside or outside the function. Here I'm going to declare it inside the counter function itself. So I'll declare another function, which takes an event. That's what the DOM passes, and in this case, React is passing a wrapped up event. And then I'll say that React handled the click. And then I'd like to output the event object. Now I click. What happened? Well, React handled the click. We saw that, meaning that function was executed. And the event being passed, notice, was not a DOM event. It wasn't a pointer event. It's a synthetic base event. And the native event, the thing that actually came from the DOM, is called the pointer event. So this is an object wrapping around the original native event. This is a React object. React calls it synthetic because it's not real. It's just a JavaScript object that React created. And inside that synthetic base event, we can see things like, yes, it bubbles. We can see the target like we did in the native event, the event that actually is included with the browser. And we can see things like tag name. But the point here is that we didn't have to do anything special in order to determine what the target was. React did that same kind of code that we wrote in the previous lecture. It has a single click event listener on main, and when I clicked the button, first there was event capturing that went down, we ignored that, we reached the target, the button, and then the event bubbled back up and eventually made it to main. The event listener inside React knows that button was the target. And in my code, I specified to React what function I wanted to run when that button was clicked. So it knew what function to run because it has that within its object structure. It has a reference to this click handler function. Make sense so far? It looks like I have a listener on button, but I don't. React is putting a single listener on main and then dealing with the fact that the target was button, running the function that I asked it to run when the event occurred on that target. You may have also noticed that my original manually added click was also run. However, I added this event listener after React added its own event listeners because React ran first. So my event listener ran later. If I had put this code before I even ran any React code by creating root, then my event handler would have run first. And then React's event handlers, which were added after mine in that case, would also be run. And in this way, we can see that the event listeners that React is creating and my own DOM code to add an event listener are essentially the same code. React is just helping us deal with events. And the thing that wraps up the event that we saw pass to click handler, React calls a React event object. And another way to say that is a synthetic event. And in our code, all we have to think about is what event do we want to handle for what target. By the way, notice that I don't have anything assigned for counter2, but it's a very similar DOM structure. So when I click re-render and counter2 is outputted to the DOM, replacing counter1, but really just some of this text above the button is changed, not the text inside this button itself, what do you think will happen? Will the click run or not? Let's try it. First, I'll click me, runs, then I re-render. Counter2 is now there, and I click, and I only get my manually added event listener. And this shows that the event wasn't added to the button element in the DOM, but rather to the root. React is aware that in the fiber tree, what I'm now outputting is counter2. So when I click button, the event delegation is dealing with the counter2 function component, not the counter function component. And so since there's no event handler on the button in counter2, now the current piece of the fiber tree, React knows to do nothing. Let's move on. Now that we understand the React event object is wrapping up the native event and helping us very simply to respond to user events, let's look a little bit deeper at synthetic event properties and methods. For starters, I'll remove my manually added event listener. We won't need that anymore. Now, we already were outputting the React event object, a synthetic event, and we saw it had a lot of properties and methods. There's a lot possible there. To demonstrate some of the things we've been talking about, though, we'll look at two commonly used ones that are really wrappers for something the DOM already does. To demonstrate, let's add some more handlers. Let's say that on the article, I'll say that on click, I want a function I'll call parent click handler to run. And while we're at it, let's add a link. A link, say, to this course at understandingreact.com. I'll open it in a new window. And again, I'll say on click. And remember, this is the on click property for this React element, which will end up being part of how the root elements event listener figures out what function to run. I'll call that link click handler. And this is just a link to understanding React. Let's make these other two handlers. A parent click handler. It will be sent an event by React. And I'll just say that the parent was clicked to. Then the link I'll say going to site. Let's try that. I can click me, and we see that not only is the click handler run, but the parent's click handler is run because of bubbling. And there is our synthetic event, a React event object. If I click the link Understanding React, I can see that it goes to the site. So the link event handler was run, and again, the parent was run because of event bubbling. That is to say, event capturing ran, but none of these on events run during capturing. It reached the target, the thing I clicked, for example, the A, and then went back up running any appropriate handlers that are registered. Of course, there's not anything truly registered in the DOM, just one listener registered in the DOM at the root. So React is mimicking what's happening with the bubbling. It's already bubbled up when it reaches the function that React is running, and the React is going from the target up, running these functions. First link, then parent, or first click handler, then parent, depending on what I clicked on. React also wraps up basic functionality that the DOM has. For example, let's add a commonly used method called event.preventDefault. This is provided by the DOM, and React wraps up this functionality, and it works essentially the same way it would if we were doing it directly in the DOM ourselves. What this does is says, prevent whatever was clicked on from behaving in the way it normally would behave when clicked by default in the browser. So for example, a link when clicked takes you somewhere. Now when I click it, although it says going to site because the event handler was run and the parent was run, the actual thing that the browser is supposed to do when I click a link didn't happen. I prevented the default behavior. I can also do something called event.stop propagation. Propagation meaning the event being captured or bubbling. So what do you think will happen if at the target level of the DOM, I prevent the event, I stop the event from propagating back up the tree? Well, I click the link and I get going to site, but the parent event handler doesn't run. The event bubbling doesn't happen. Despite React's event delegation, we get the same behavior inside React as we would if we were doing this in the DOM manually. Note that these examples show that even though React is wrapping everything up inside a React event object, and it's actually registering a single listener by default at the root, we can rely on how we understand event capturing and bubbling to work. We can prevent the default behavior, we can stop the propagation, and we can rely on the propagation with our handlers. And of course, onClick isn't the only event by far that I can respond to. In this way, I'm starting to build an interactive application. React is updating the DOM as needed and also enabling me to respond to events. And as we'll see, These basic inputs and outputs, events coming in, DOM updates going out, will form the foundation of what we're doing. And there's one more piece in between that we'll now need to understand. We'll see how events and DOM updates are related through state. But first, we need to understand what we really mean by state and how React wants us to think about it. Let's move on. In this section, we talk about the concept of state in programming in a way that will set us up to properly understand how React utilizes and implements state and how we can do so in our React applications. In this conceptual aside, we dive in to the concept of state machines, and that will set us up to understand how React implements and uses the concept of state. When we say a state machine, think about the fact that the computer is really a machine. It's a physical device, and we, the coders, are giving instructions to it. So going back far into the history of computer science, when we say the word machine, that's what we meant. We meant a physical device. For most of us coders, we aren't that close to the hardware, though. We're dealing with layers and layers of abstraction before we get to JavaScript. Nonetheless, the core underlying concepts are still necessary and incredibly useful to understand. So for starters, big word alert. State. In the context of software, when we say state, we mean the data, the information at any given time that defines the current state, or that is to say the current condition of the system. So for example, if I'm talking about a stoplight, the state of the system might be a combination of, is the stoplight red, green, or yellow? How much time is left on some countdown timer that's saying how long until the light changes? And some sensors in the road saying, are there cars sitting there waiting or not? Altogether, that would be the state of the system. Or another way to think about it would be that if it was a stoplight, the state of the system is simply red, green, yellow, and the countdown timer is some kind of external system, and sensors as to whether cars are waiting are inputs for some future check to see if the state, that is, the light, should change. When we talk about state machines, we're usually talking about finite state machines. Big word alert. A finite state machine. A finite state machine is a model. It's a model of a process that can be in a limited number of states. It models the states, the inputs, and the transitions between states in response to the inputs. In the case of a stoplight, the states might be red, yellow, green, and the inputs are how long have we been waiting, and is there a car waiting? The transition would then be from moving from green to yellow, yellow to red, etc. When dealing with our code, we generally are also dealing with deterministic finite state machines. Big word alert. Deterministic. The deterministic process is predictable. That is to say, in the context of a state machine, you always get the same output given the same inputs and state. If I start with a certain state and I give a certain input, I'll always get the same next state. It's deterministic. I can rely on it. Let's think more about our example. We have a stoplight. It can be green, yellow, or red. Those are states. For example, for the stoplight going from north to south, we might say that the state currently is north-south green. And then there's some external, we could say asynchronous process of a timer that's counting down. It started at 30 seconds, let's say, that the light will stay green. So north-south green, and the timer should start counting down. When it hits 0 seconds left would be an input that would cause a state change. We, of course, are interacting with the system. So cars are moving from south to north and north to south because of the state of the system. And cars moving east to west and west to east are not moving. They're stopped, also because of the state of the system. If, however, a car comes and waits, perhaps our system is coded to say, well, as soon as the fact that a sensor detects that a car is sitting on the road waiting for the light, we'll change the countdown to say, well, we should wait at most 10 seconds. So the current state is that there's an east-west car waiting. And we're waiting for at most 10 seconds to pass. If 10 seconds has already passed, then the state should change. Suppose that happened, then the new state would be north to south is now yellow. We're about to change north to south to red so that east to west can be green. And that should only be, say, 5 seconds. Once the 5 seconds has passed, we set a new state. The system is in a new state, north, south, red. And again, let's say it will stay red for 30 seconds. And we again are interacting with the system. A stoplight at an intersection is an example of a deterministic finite state machine. And we can draw the flow of those states. Our light may start out in a condition of green with a 30-second timer. But if an input changes, the car is now waiting, that timer changes to 10 seconds. 10 seconds in that state passing means that we move to yellow, or 30 seconds from green also means we move to yellow. Yellow always waits 5 seconds. Yellow always changes from yellow to red. And red always waits 30 seconds, and red always changes to green. Note that this is a state machine. It's a sequence of unique states with transitions from one to the other. And it's finite. There's 4 possible states. There's not an infinite number of possible states. And it's deterministic. If I'm in the east-west car waiting state and I say 10 seconds has passed, I'm always going to see that the next state is yellow. Or if I'm in the red state, I'll always know that the next state will be green no matter what. We rely on the fact that systems like stoplights at intersections are deterministic. We never have to worry that a red light will move to yellow. We'll never have to worry that a yellow light will move back to green. If you live in a country where the stoplights are red, green, yellow, or if there's some other common way of determining how cars and traffic should flow, whatever the case, we are surrounded by and depend upon deterministic finite state machines every day. And understanding this will help you understand React. It's time for another conceptual aside. And this time, the idea of finite state machines, deterministic finite state machines, helps us to understand the importance of pure functions. Let's think again about our intersection. We understand that we have the current state of the system. But every now and again, some process is going to check how much time has passed. We can think of that as a function. It's a function being called on a regular basis. Let's call it check time. On a regular basis, this function will be called and look at how much time has passed on a clock. We can think of that clock as running asynchronously to our finite state machine. And it's important that that function is pure. Remember, a pure function doesn't change any of the data, the information, the variables that are passed to it or are outside what's been declared inside the function. So if the timer is outside the function, it would be a big surprise if calling check time reset the timer, for example. If we think about it this way, check time is a function that has inputs. For example, how much time has passed, and is there a car waiting, true or false? And inside that function are commands, pieces of logic, deciding should I change state or not, or should I output the same state the system is currently in, no state change. Whatever the case, the next state after being checked is what will be output. But if we had a bug in our code where the function touched something from outside itself, if it changed a value that was passed into it, for example, like it changed the time passed input to 0 seconds, resetting the timer, forcing a state change before it should, then what would happen is, if the light was red, for example, as soon as check time was called, instead of waiting 30 seconds, it would immediately change to green. And the next time it changed to red, it would change right back to green again, and people would be very frustrated coming the other direction. If check time changed the value of time passed, it would be an impure function. It's even possible that our system would no longer be deterministic. For example, if the logic and the bug caused time passed to be changed sometimes and sometimes not, we'd get a different state out despite having the same inputs in. Pure functions help make sure that our state machine is deterministic, that it stays consistent and predictable. React exists to help us build user interfaces. And so understanding finite state machines helps us to understand how React thinks and wants us to think about state and UI. First, big word alert, UI or user interface. When we talk about the user interface, we're talking about what the user sees, hears, or otherwise interacts with. And we already have been looking at an example of a user interface when we've talked about street intersections. We have these inputs, we have some code, and we have an output that ultimately is what the user sees or hears or interacts with. In this case, the traffic light. The traffic light is the user interface. The user interface is a function of the state. Whatever the state is of the system, that is what the user interface is reflecting. And for the user to then experience a reliable, predictable interface, the underlying state machine needs to be deterministic, finite, and reliable. React says the same thing about our components and the user interface. There's some state, the data, the information that defines the system at the moment. For example, how many times a button has been clicked on. There's the functions that are being called, which should be pure. These functions make up our components that we've already seen. React is invoking those functions when it decides it's needed. And finally, the output, the results of the state, is a tree that defines the user interface. So from React's perspective, the user interface is a function of state. In other words, our component functions are called, they're given that state, and the output is our UI. And this should be deterministic. If I give the same state to our React components, I should get the same tree as a result. Make sense? That fundamental concept underpins how React thinks about state and implements it. So as we move on to look at exactly how that state is implemented and begin to use it, we can think about how the tree is being generated as a function of state. And thanks to our functions being pure, not changing the data that's being passed to it, the state transitions, how the UI changes over time as the state changes, is predictable and reliable. It's time for another conceptual aside. This time, we talk about reducers. Reducers are a concept that comes from functional programming. Big word alert. Functional programming. This is a style of programming where you organize all your code into pure functions. While writing React code isn't writing functional programming, React borrows a lot of concepts from functional programming, the functional programming style. Our components are pure functions, and all of our components are functions. Functional programming is super powerful, and turns out that these concepts can have a lot of use within how browsers work in writing code for the browser. JavaScript lets us write in a functional programming style, and some functional programming concepts have been embedded into JavaScript itself. One of those concepts is a reducer. I'm going to get rid of all of our React code for the moment and just talk about reducers. I'm going to make an array, just 4 numbers. And a reducer, when we say a reducer, it's really an approach, a construct for dealing with a set of data or a set of things, in this case, an array. A reducer lets us take all of the items in a list and continuously act upon all of them in a loop, often with the goal of reducing all of the values in the list to a single value. How the items in the list are acted upon is something that we define with our own function that will be passed to the reducer. Our function will be called by the reducer as it loops over the list. As it loops over the list, it will pass to our function when it calls it what we call an accumulator and the current value that is the thing that we're on in the list, the actual item in the list that we're currently looking at. The accumulator is whatever's returned from the last time our reducer function was called. So our reducer function will be called 4 times in this case. one for each time in the list. And every time it's called, the accumulator value that's passed to the function will be whatever was returned from the previous time our reducer function was called. I'm going to put some logs here so we can see what's happening. I'll say that we're on a particular iteration just to make it clear. Say what the accumulator is. The value that we're currently on in the list. And now I need to return a value. And again, the value I return will be passed as the accumulator the next time the function is called for the next item in the list. So I'll say the next accumulator. In my case, I'm just going to add up all the values in the array. Now I'll log this as well so we can see what's happening. And that's what I will return. Now to use it, I'm going to set an initial value. Remember we said the accumulator being passed as the result of the previous function call, and when you start on the first time, the first item in the list, there is no previous function call. So a typical reducer function will let us pass an initial value. I'm going to get a sum. I'll take the array, and within JavaScript built in on arrays, there's a function called reduce. It takes the function that should be called as it iterates over the list and an initial value, if one. Then we'll output the final sum. Let's think about what's going to happen here. JavaScript will run this reduce function, meaning it will go through each item in the numbers array, calling the reducer function that we created until it gets to the end of the list, and it will return that last accumulator. Before I do that, I have a little typo here. Visual Studio Code helped me with that. And the same here. There we go. Let's run this. Here I see the first iteration. The accumulator is the initial value, so my reducer function was called by the reduce function, passing the initial value. It looks at the first item in the list, which is a 1, adds 1 to 0, and returns a 1. The next iteration, what was returned from the previous 1, is passed as the accumulator. The current value is the second item in the list, which was a value of 2. In my reducer function, I add the 2 together, so I get 3. And that's what's passed as the accumulator to the next function call and the next. And then it's finished with all the items in the array. And the last thing returned from my function was 10. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. So it reduced. So I wrote a function that allowed me to reduce my arrays to a single value. I could have done the same thing, but in a completely different way. What if I just put string concatenation instead of adding the two numbers? Then I see that I get a very similar result, but the accumulation is building up a string instead of adding up the values. And there I get my final string, which includes the initial value, even though it wasn't in the array, because that's the initial value passed when I called reduce. Make sense? This idea of a reducer is necessary to understand how React implements state and transitioning between states when you're building your own systems. Let's move on. Thinking in terms of state machines, we're thinking in terms of the state transitioning. We're in a certain state, and the next state is the one we should be in thanks to the inputs. How do we model that? Thinking again about our state machine that we looked at, for example, we can see how the state machine should behave. But what about those arrows? How do we model the transitions? How do we model the changes? How do we code our system so that it's easy to understand how the deterministic finite state machine works and use it? There's an approach that's very popular. So popular that React has embedded it into itself. That approach is called actions. Big word alert. An action. In this case, in this context, it's a description of what has occurred in an app and how the state changes as a result. In other words, we can model that something happens in the app, a button is clicked, etc., and what information then changes, what inputs change to the functions, and how the state should then change. However, we still need to understand what we pass the action to. How do we model the states themselves? And we think back to this idea of a reducer. A reducer works against a list of items, reducing them down often to a single value. And if we change our mindset about states, if we think of them as a list of items, but a list of items that appear over time, then we can see we can also think of them as something that can be reduced. If I start off with green north to south, and the car is waiting, and then time passes, and then it goes to yellow, and now 5 seconds has passed, I can reduce all of those concepts to the final new accumulated state, that of north-south red with a 30-second wait. North-south red is an accumulation of the other states. You don't just jump to that state. And each action is a call to the reducer function with these new inputs, these things that happen. So we'll take the idea of a reducer and the idea of state and model something that makes it easier for us, the developers, to manage our state and actions, that is, the things that can happen in the app together to move from state to state. I'll start by setting some state, just a JavaScript object. We'll use the example we've been using of a traffic intersection. We'll make it extremely simplistic. We'll say that we're just interested in north to south. That will be green, yellow, red. We'll say, is there a car waiting? It'll start as false. And then how much time should we wait before transitioning to the next state? Now I'm going to write a reducer function. It will take what is being accumulated. That is, what's the previous results of the previous call to the reducer, which will be the previous state, and the current value, which is going to be another object we'll call the action, and that will describe what has happened in the app. So we give the reducer the current state and whatever has happened in the app, and we should get out in a deterministic, predictable way what the next state should be. And that can keep working over time as we move from state to state, depending on the actions. For our simplistic example here, I'll use a switch statement, and my action will be a JavaScript object. In that object, I'll have a property called type, which will just say what type of action has occurred. For this simple example, I'll just make it a string. So let's say that I say to the reducer, a car is now waiting. That's the action that happened. And so now it's going to give me back a new state. Because I want the reducer function to be pure, it shouldn't change global state. It shouldn't edit it, mutate it. Instead, I'm going to return essentially a copy of global state with the appropriate elements added or changed. I'll use the spread operator to grab all of the individual properties from my global state, and then I can overwrite them as needed. I'll say car waiting is true and a new wait time. I'll let the action tell me what that is. A standard way of saying this is that the action object has a type and a payload. A payload, for example, is what we call what a truck is carrying. It's carrying a payload. It's the thing that's being delivered. So in this case, the action might be delivering some pieces of data along with the type of action that's being carried out. This can make it very easy for me to update my states appropriately and track what's happening in the app. So this will return a new object with north, I meant this to be south, north, south, green. Car waiting will end up true. It will overwrite this one, and wait time will be whatever's attached to this object that's passed in. Another thing that can happen is that we've finished waiting. Maybe the timer has finished up. And so we pass to the reducer that that action has occurred within the system. And again, we'll grab whatever the state passed in was, but we're creating a new version so that the function is pure, not mutating the value of the parameters, the arguments that were passed to the function. And then I'll just change the north-south to yellow. And then by default, if no action that we want to make changes on is passed in, I'll just return the state that was passed in, no state change. Let's try using this. First, we'll log whatever the global state is. That's our start. I'm going to get a new state by calling Reducer. I'll pass the global state as our initial value, and I'll pass the action. The action will take a type, let's say car is waiting, and a payload. I'll make that an object as well with the wait time of 5. Then I'll log that new state. Then let's say we take that new state and call Reducer again, this time saying that, let's pretend we finished waiting for the timer to count down, and we'll output that. Let's see what we get. Here's the initial state, the global state. Then after my first action, here's the new state, green, but the car is waiting and it's a wait time of 5 seconds. And then after that, the next change that we finished waiting, we end up with the car is waiting is true, and now it's yellow, and then it's 5 seconds. And I could go on from there to model my intersection. This isn't an array, but it is a sequence of states being generated over time. The action provides a very clean way for me, the developer, to lay out all of the things that can happen in my application and update the state accordingly. And because it's pure, I'm not worried about the bugs that an impure function can cause. It's always returning a new object, so I know this is a new state. Make sense? We can then think about everything that happens in our application as a sequence of actions where we reduce the beginning state and the sequence of actions down to the current state through whatever state transitions happen in between. We've reduced our global state in this case to this final new state 2 after saying that we finished waiting. This turns out to be a very, very clean way to describe and track what happens in your application. And as a result, not only have various systems been built on top of it, but React has embedded this concept within itself as a tool that you can use for managing the state of your application. But not just state globally, but also you can think about state as far as what state is needed at any point in the tree. Let's move on. In this section, we take all that we've learned about how React is structured and the fiber tree, and we combine it with what we just discussed about state, and we come to understand how React works when it comes to state, and more generally when it comes to a concept that React calls hooks. This is hooks and state. Let's talk about where state lives inside React and how it relates to the fiber tree. This is fiber, hooks, and state. We've talked a lot about the fiber tree, a tree of JavaScript objects that describes what the DOM should look like and contains the function components that we create. And so now, here's a question. We know that the fiber tree sticks around, so that means it's a good place to store state, to store any information that the tree depends on. But how is that state stored? Where is it stored? It's stored in hooks. You can think about a hook kind of like attaching something to the tree, like you would a bird feeder. A hook is attached to a particular fiber node, hanging on the branch, so to speak, of the tree. To reach that particular hook, you need to be on the right branch. And that's exactly what React is doing. That's the way it structures what it calls hooks. Hooks are directly connected to fiber nodes, but they aren't really part of the tree. They aren't nodes of the tree. they're off to the side. They're things kind of hanging off of the nodes. I went back to our React code that we last had. Then running it, I've commented out some of the extra statements that we placed into React DOM. And I'll just open this first fiber node, the fiber root node. Its child is a fiber node whose type is our app function. So that's the top of the tree that we've been creating with JSX. And notice that all along, we've been seeing a property called memWiseState. At the time of the recording of this video, that is where the state is stored for any particular fiber node. Each fiber node has lots of different properties, and one of them is state. State will end up being a JavaScript object we call a hook. Inside that object are a few things. For example, the S here stands for state, and the Q is something we'll look at in just a moment. Suffice it to say, the hook is a JavaScript object. I'll draw your attention inside React-DOM to a function that at the time of the recording of this course is called mountWorkInProgress hook. It's attaching a hook to the work in progress fiber, to that node. And notice what the hook is. It's just a JavaScript object. In fact, it has its own state. Again, the fiber node has state, which is pointing to this hook. And the hook itself inside it has its own state, as well as something called a queue and a next property, where next points to another hook. That means the way React has designed this, each fiber node can have its own state. It can point at its own hook, and each hook can point at another hook, at another object, and so on and so forth. It's yet another linked list attached to a node of a linked list. So these hooks, once again, are stored in very simple, lightweight data structures. And each hook has its own state property. And each fiber node can have one or more hooks attached via this linked list concept. This is the basic mental model you should have when thinking about what hooks are. They're just JavaScript objects attached to JavaScript objects. That is, hooks are attached to nodes of the tree. And in all cases, we're dealing here with linked list. They point to the next one in the list. Let's move on. It's time for a conceptual aside. This time we talk about queues. Big word alert. A queue. A queue is a simple data structure where a list of items is first in, first out, or FIFO. That is to say, items are retrieved in the order they are placed, one at a time. If you're in a line at the grocery store, the first person in line is the first person who will get to check out. And then the second person, the third, and so on. The first one in is the first one out. So visually, as items are added to the queue and then removed from the queue or retrieved from the queue, they'll be retrieved in the order they were added. A good way to understand a queue is to build one. It's a type of data structure, just like our linked list. In fact, we can use a linked list as a base and build a queue on top of it, although you could implement a queue in different ways. So I'll take the linked list code that we created earlier in the course, and we'll still have linked list nodes, but the primary data structure we'll call a queue. We'll still have the head and tail. We'll still append things. But the question is, now we want to be able to remove items. And so if it's a queue, often that's called popping an item off of the queue. That means the first one in, which would be the head. Remember, the tail is the last item of the linked list, and the head is the first item. So I'll need to say, I'll store the head of the list, make sure there is one, and then say that the new head of the linked list is the next item in the linked list. Essentially removing the first item from the linked list. There's no more reference to it. And then I'll say that as long as we still have one, get its value. Remember that a node had a value and a next property. And that's it. Every time I call pop, I'm going to get the head of the linked list. And then the new head will be the next item, essentially removing that item from the list. Let's call this a queue, and we'll call this my queue. We'll go ahead and append these 3 items. And now this is first in, first out. So Tony, Alicia, and Understanding React in that order would be popped off the list. That is to say, removed from the queue. Let's call the pop function and return its value. And let's go ahead and do it again. Each time, this will return the current head of the linked list, and the linked list itself will be shorter by 1. And I'll print it after popping 2 values. What should I see? Well, I see my initial queue, 3 items, and then first in, first out. The first one popped is Tony. That was the first one in. The second one, Alicia. That was the second one in. And what's left over in the queue is what was left after those were popped. A queue is a simple way of saying, I want to store these items, and then I want to process them in the order they were added. In this lecture, we take a look at another piece of what's inside each hook and on each fiber node. This is update queues. When we were looking at our fiber nodes, we noticed that there was memwised state, and there's also an update queue on each fiber node. But inside each hook, there's also state and queues. So while we have state, we also have on each hook a linked list that forms a first in, first out list of items, a queue. So in our mental model, we go beyond just the state, but there's also the ability to line up a series of things that need to be worked on at some point in time via a queue. That is to say, we can line up a bunch of work and eventually flush the queue. Big word alert. Flush. In this context, we mean to empty a data structure of its data and deal with the data. So we're using the queue to set up work that eventually we will handle. React does this, and it allows it to deal with updates to state that we request when it decides that it's best to deal with them. For example, React can batch updates. Big word alert. Batching. That means processing multiple tasks as a single group. So, for example, you may request that state be updated in multiple hooks within your component, and React can choose to update all those hooks as one process, rather than updating each hook separately and then letting React continue to run its other processes and then updating another hook. By each hook not only having state but having queues, React has more flexibility to be more performant. While the internals of hooks are a bit more complex than this when we look at state, and even when we look at queues, our goal is to have a strong mental model. And this is a strong one. At its most basic, hooks are state attached to each fiber node, and really a linked list as one hook connects to another each time you use one. And inside the hook, it also has its own state and queues, which are also linked lists, essentially first in, first out, which provides flexibility for performance. So the next question becomes, how do we access these hooks? How do we create them? How do we update them? How do we use them in our code? Well, we're almost there. Just one more note about what happens when you update state. That's next. We've said that UI is a function of state, and that means when the state changes, the UI should change. This is state and re-renders. We know now that this is the basic concept of what the React fiber tree and hooks looks like. Let's imagine a scenario like this. We have a component called counter and a component called list. And both the app itself, at the root, the list component, and the counter component are using hooks. In this case, the hooks are being used to store data, the state of the application. But here's a question. Up until now, we've been manually creating our own button to ask React to re-render, to call the components again, run reconciliation, figuring out the difference between the DOM tree and the new tree, using the fiber tree in between, and making those updates. But that's not how we want things to work in reality. We don't want to manually have to hit a button to ask React to update. The thing that should happen that causes React to update is that state changes. If the tree is the output, if it's the function of state, then when state changes, we know the tree should at least be checked to see if it should change. If we imagine our state, for example, being the number of users logged in being stored at the app level, the number of items in the list being stored in the list component, the number of times that a counter is clicked being used in the counter component, we don't necessarily have to re-render the entire tree. We need to re-render the portion of the tree that depends on a particular piece of state. So if the state in the hook attached to the list component changes, then the list component should re-render, that is, the function should be called again, which will call all of its children functions as well. But if the times clicked changes and that's attached only to counter, then only counter needs to update. That's the most simplistic approach to thinking about when updates happen, when state changes. Where does state live, which informs what piece of the tree should potentially be updated? The nice thing is, this can happen automatically just by us updating state. React then knows that the tree should be checked for changes. In other words, our function components should be executed again to see the final output, to see if it's different from the current DOM tree. This is how React thinks about state and how it wants us to think about state as well. It's now time to take everything we've learned so far and begin to understand how to use the features of React that allow us to manage state, and in so doing, make our components fully interactive. This is useReducer. First, we'll set ourselves up with some simplifications. I'll get rid of these calls to counter and just have a single counter for now, just the one. Get rid of all these click handlers. And we'll even simplify. We won't destructure the props object, just to show that you can also just use props as an object directly. Get rid of the extra thing here. We'll get rid of the second counter, and we'll get rid of this re-render function. We got rid of the button here in the index.html for it. We'll never use this again. We're going to let React decide when to re-render. That will be a declarative instead of imperative approach. I won't tell React, please re-render. By the actions that I take, React will choose to do so. I'll also get rid of the onClick for the moment, since I got rid of the handler. And now, for the first time, we'll use a hook. React provides hooks. Each are individual functions that will create a hook added on to the fiber tree and has a specific functionality. React named all of its hook functions starting with the word use, so you can recognize quickly that that's a hook. For managing state in your application, the most basic hook is useReducer. So what is useReducer inside React? Well, if I go inside React's source code, I find that it's just a function. It takes a reducer function that we define. It also takes the initial starting value and one more parameter. That ends up getting passed at the time of the recording of this video to mountReducer, which is going to add the hook to the fiber tree if it's not there. And notice that that third argument can actually be a function that will be passed the initial value, and then that will become the initial state. And if we don't pass a third argument, then the value passed as initial arg will be the initial state. The hook will have its state then set to that initial value. And then it sets up a queue. The queue has our reducing function that React will eventually call. And the queue also has something called dispatch. Big word alert. Dispatch. The idea is that we're simply sending the action to the reducer. We're saying this action has happened, so the reducing function should be called so we get the new state. So there's this idea of dispatch also attached to the queue, which is another function within React. The reducer action is dispatched, and it expects what fiber we're on, what the queue is, and our action. And then it will do work to schedule that work happening. If I go back, we see that it uses .bind, which in this case is used to always pass the fiber and the queue as the first parameters to this function call, and then we'll pass our action as a parameter. Notice that fiber and queue were the first ones, so that's passed by React via .bind, and then when we call dispatch, we will pass this third parameter action, but it will look like just one parameter to us. Finally, we see what we get back ultimately from useReducer. We get an array. The array has two items. It has a reference to that memwise state inside the hook, so the state in the hook, and a reference to this function call where the appropriate fiber and queue will be passed to it. We can then execute this dispatch function, passing it our action, which will then cause our reducer to be run. That means that what we get back, well, we'll just name it state and dispatch for clarity. We'll get back the current state, which is a reference to what's inside the hook object sitting on the fiber tree, and the dispatch function, which will already be past the appropriate fiber node, and the queue from our hook. We pass to useReducer a reducing function, and we can also pass the initial value. For our counter, I'll have an object that stores the number of clicks. This way, I can say state.clicks. Note that I passed the initial state to useReducer. It set that initial state as the state of the hook, and then gave that state back to me in this array. I'm using array destructuring here, so I can pull the two values returned from useReducer inside that array into two variables. I'll also remove the article on click, and let's try running this. Well, everything runs just fine, but nothing happens when I click the button. Because I haven't hooked up anything to happen, I removed the on click, but I can see that the state was set appropriately. But more than that, let's go back to our fiber node. We'll go down and try to find counter. This is app. Here's child. Child is an H1. And the sibling of the H1 is a section. And the child of the section is my counter function. Since I declared the hook inside this function, the fiber node created from this function should store the hook. If I look for memwise state, it's no longer null on this node. If I open it, there's my initial state. Click 0. And there's my queue with the dispatch function that I can then call. So my component, which is counter, has a hook attached to it via a property. And the hook contains my state and the function to update that state. And when useReducer returned this state, it was then available to be used inside my JSX, which is really just more function calls. Inside this function call, inside this text, I had access to this JavaScript object, which has a property called clicks. And that, at the moment, is 0. Let's move on. In this lecture, we take a look at one of the most common hooks used in React. This is useState. Most React tutorials and courses start you right off by using this hook, useState. But I first showed you useReducer. There's a reason for that. useState is really just a specialized version of useReducer. If I go into React source code and I find the useState hook, when it mounts the state to the fiber tree, it sets up the exact same structure as useReducer does. Whatever you pass as the initial state is stored on the hook. And then there's a queue created that holds a reducer that dispatches. It's exactly the same. In fact, you return a dispatcher from useState, the state itself and the dispatch function. Again, just like useReducer. The difference is we don't pass a reducer function to useState. We just pass the initial state. React has a built-in reducer function specifically for useState. It's a reducer function, so it takes state and action. And while our reducer functions take the action and then decide what to do with the action, returning the appropriate state, this simple state reducer instead looks at your action and sets that to be the state. Unless your action is a function, then it will call your function and return the value from that instead. We'll see that a bit later. For basic usage of useState, if you pass a string or a number, for example, or an object, it's being passed to the reducer function as the action, and then the state itself is the value of that action. Let's try using it here in our app. I'll replace my call to useReducer with a call to useState. It only takes the initial state. Let's start that as just 0, the number of clicks. I get back a reference to the state stored on the hook object, as well as the dispatcher. But we're not really looking at it as a reducer function. That's happening at a level below, in this case, inside React. So by standard or convention, we tend to do this. We'll say set whatever the state is. And then this is now a function that I could pass the state to. I changed this from an object to just a numeric value. So I'll just say num of clicks here. And I'll get rid of the onClick for now. Let's see if this works. 0 was attached as the state, and here it shows up in my component. When I go into the fiber node, I go down and find my app function, and I'll keep going because I'm looking for the counter. There's the h1, sibling is a section, and the child is a type of my counter function. I'm looking for memwise state, and there it is. It's not an object, it's the numeric value, 0. And on the queue is that reducing function that was built inside React instead of me passing to it. The state has been set on the hook, and if I call set number of clicks, then it will run that dispatch of the action, which will run the reducer inside of React and set the state to the value of the action that I pass, which is really, in that case then, passing the new state. Let's see that next. In this section, we keep talking about useState. Let's update our state on the click of the button. I'll say on click, and then some JavaScript, and I'll have a function that calls set number of clicks, and I'll pass to it a new state, which is the number of clicks currently plus 1. In reality, this will call a reducing function with this as the action, but the state will be set equal to the value of my action. Let's give it a try. There it is. It works. The state is updated when I call set number of clicks, which is really a dispatch function. And it directly updates the state to be whatever I passed to that dispatch function. And here I have a stateful component. But as we saw, useState is really just a wrapper for useReducer for simple cases. As soon as your state becomes somewhat complex to deal with, you should probably be using at least useReducer instead of useState. However, at the beginning of this course, we did say we'd get to the point of a particular app where we have multiple counters, each one keeping count of its own number of clicks. And we've arrived at that point. I'm able to simply drop a second counter. I'll pass a different name as part of the props. And now let's see if you can work out what's happening here. Two different counter functions will be executed. They're being passed different props. Each one will result in its own branch of the fiber tree. And each one, because a hook is called, will have a hook object attached or mounted to that node of the fiber tree, each counter being its own node. So each one will keep track of its own state. When React then reconciles by generating the React element tree and the fiber tree, and then comparing to the current DOM tree, we get our result. Our UI is a function of our state. So if I update counter 2, it shouldn't update counter 1. Each one is its own state. So I click, counter 2 works, and so does counter 1. We made it. We've gotten to where a lot of tutorials and courses start with React. But I hope you appreciate so far the importance of truly, deeply understanding what React is doing. Just seeing these click me buttons work and update the counter is a lot deeper than we might imagine. And understanding the JSX that we're writing and how everything works together helps you to both understand, write, remember, and debug your JavaScript code that's intended to be used by React. Another piece of the puzzle that we're seeing along the way as we've learned about useReducer, useState, and props is that when we attach state to a fiber tree, and part of that state is passed down to the children, and as we update state, we see where the state lives and the children of that state being re-rendered, that is, the functions being re-executed. We're seeing an example of React's unidirectional data flow. Big word alert. Unidirectional data flow. That means that data can only move in one direction. In the case of React, data only moves down the tree, never up. For example, if I take a counter component's JSX and drop it into Babel, I can see that there are children being passed as a property of the props object. Props always has this children property. I can see it if I just start looking at the fiber nodes. For example, on the H1, which is counters, I see that there is a prop to that internal React component, the standard H1 element. It's an object and has a children property. But I can keep going down, find my counters, and see under memwise props that the props I passed as well are there. There's no children property, however, because my counter has no children. It's a self-closing tag here. There are no child elements in the JSX, meaning no other functions are being called as part of counter. However, if I go back up and find section, the section fiber node does have children. It has two children. Each of my counters, the first counter and the second counter, which has its own props. So just looking at the counter component and what it's transpiled into, we see that an article function is called, passing children, which is really an object with a children property. That's the props object. And so on and so forth down the tree. The H2 is called, and the P is called, and there's a button that's called, and they're being passed these properties. When the data is updated, the counter is called again, and all of its child components, all of its ancestors, are also called. Notice that props is never passed up. That wouldn't make sense the way React is transpiled. It's function call inside of function call inside of function call. So arguments are simply passed down through the function calls. In this way, you never have to wonder or think about what is happening with a child in relation to its parent as far as is the child updating the parent. The parent is always calling the child. Data flows in one direction. Way down at the bottom, in the button component, there's a click event that calls a function. But where did the function come from? It was given to button by the parent, the counter. And so when this button function runs, it's using the data given to it from a parent. And that reference will then update the data in the parent, which will cause all of these functions to be executed again because state is changed. But notice that button doesn't directly update the value of the state in counter. It doesn't directly update the value of state in a parent. The parent has to give it a reference to a function, but that function actually lives where? On the hook on the counter fiber node. While a parent can give a child the ability to update some parent data, it isn't really doing it directly. It's just giving it a reference to something the parent, owns. The data is unidirectional. Data lives in one part of the tree and is passed down to its children. Data never lives in a child part of the tree and is passed up to its parent. This is a fundamental aspect of how React works and how we think about React applications. It's one of the reasons React became popular, because it was easier to reason on when you know that data only moves in one direction. So that's unidirectional data flow. Now, there's one other thing to talk about. I want to show you what happens when we add multiple hooks. So I'll just create some hooks, but I won't use them. I just want to see where they're stored. We saw an example of this already, but let's look at it now that we're using these hooks. And I'll use even multiple types of hooks. I'll use a couple of useStates, and I'll use a direct useReducer. I won't even really put anything in the reducing function, but I'll just give it my last name as the initial data. So now I have 3 hooks, a useState with a value, a useState with another value, my first name, and a useReducer with my last name as a value. Here in the fiber node of my first counter, and notice that because it's a linked list, the sibling will be the other counter, counter 2. But in this first counter, for example, I find my memwise state, which is the hook. And the hook has a next property. It's also a linked list. So memwise state is 0. That's the first use state. I go to the next hook in the linked list, and the memwise state is Tony. And I go to the next one, and the memwise state is Alicia. So we see that the first call to the hook mounted it directly on the fiber node, and each subsequent call mounted it as the next hook on the linked list stored on the fiber node. Hooks are linked lists. And when this function is called again on a re-render, it will see that those items are already there and won't have to recreate them. So we now have a clearer picture of utilizing JSX to generate a React element tree, which in turn generates a fiber tree, which holds linked lists of hooks, and ultimately, thanks to reconciliation, causes the DOM to be updated, that we have our simple app. Our simple app that tracks state. What do you think? I hope you, like me, appreciate the power of breaking down our application UI into reusable components. I only had to add a second counter in the JSX, and everything worked, state, interaction, and all. React set it up all for me properly using the fiber tree and the reconciliation to the DOM. I could add as many counters as I wanted, and they would all work. However, now that we've seen how everything is structured under the hood, it is important to recognize some rules that we must follow when using hooks. But understanding how things truly work, understanding React and hooks, you'll see result in the rules making sense. When learning about React and hooks, we learn that there are rules we must follow when it comes to using hooks, and oftentimes people go about memorizing them. But when you understand how things really work, you don't have to memorize the rules. You can derive them. Big word alert. Derive. To arrive at an idea by logically extending other concepts. So we can take one concept, work through extending it logically until we reach another concept. In this case, the internal structure of React allows us to derive the rules of using hooks. We know that hooks are attached to individual fiber nodes. Let's simplify the case and look at where it's simply the linked list of hooks attached to a node, and we're using the hooks in our code inside that particular component. What's actually happening? React is it's executing our function component, passing the appropriate props. So React is focused on that particular fiber node. Then it reaches the line where we first use a hook. And so React is it's using that particular object, the first one in the linked list. As we move on using different hooks, React is moving down the linked list every time we use a hook. So a call to useReducer, a call to useState, we'll be moving on to the next hook in the linked list line. So let's think about the two baseline rules of using hooks. Rule 1 that's often memorized is you can only call hooks from a component. You can only use a hook if you're inside a function component. And of course you can. And of course that's true, because we understand that hooks are actually objects attached to the fiber tree node created ultimately by our component. It wouldn't make sense to call it anywhere else. In fact, I bet because you understand how React really works, you would have never thought about trying to call it from outside a function component. Understanding how things really works also gives us a better instinct. Our mental model is accurate, so our assumptions are accurate, so our instinct for how to use something is correct. Now, here's another rule that people memorize. You can only call hooks at the top level of your component, not inside a condition, inside loops. In other words, you can't call a use something inside an if statement or a while loop. And if we think about how React is working, it makes sense. Let's say I did try to put a call to a hook inside an if statement. So React is calling the function, and on my first call to a hook, it goes to the first element in the hook link list. And then it's checking to see if some value is true or false. Let's suppose that that value is true. Then it's going to go ahead and go to that second item. It's going to create that hook. Let's say this is the first time the list component is being called. It's the initial render. And then it'll move on to the third one. And now we have 3 hooks in a linked list attached to the fiber node that represents our list component. But let's say list is re-rendered, state is changed. Maybe state in the app component changes, and so list is re-rendered. Or we set, by using a dispatching function and action, a setting of state, that one of the pieces of state stored in list is updated, and React is going to re-render. So it looks at the first hook that already exists, and then in the if statement, it says if some value, and let's suppose this time, on the second render, it's false. So it skips that call, and it goes to useState, and where is it going to go? To the next hook in the linked list. But this time, instead of the third one, which is what it did on the first render, it will go get the value in the second hook, the second item in the linked list. The behavior would be inconsistent. And as we've seen before, that is very undesirable. That would introduce a lot of bugs. It simply isn't something you should do. And so it's a rule of hooks that no matter how many times we call the function, we're calling every call to every hook. hook. You can't skip a hook across renders. You can't skip a hook the second time or the fifth time or the seventh time that a function component is executed. Make sense? If we keep our mental model accurate, we can derive these rules naturally. Let's try doing it incorrectly real quick. I'm going to declare const my name, const set my name, and then I'll say, let's suppose if number of clicks is less than 2, I'll set the state. Then I'll just output my name and this state variable from useReducer, which starts off as Alisea. And I'll just set both of these to empty values for the moment. And finally, I'll change these to lets, not const, so they can be changed. Now we see Tony and Alisea and click 0 times. Say 1. My function was executed again. 2. And it's not working. It looks like I got an error. If I go up, I can see that work was being done, but then at some point, the first error I see is a warning. React has detected a change in the order of hooks called by counter. This will lead to bugs and errors if not fixed, and then says to read the rules of hooks. We can see that the previous render was useState, then useState, and the next render, the one we were working on, was useState and then useReducer. We can see that useState, then useState, but once it was number of clicks was 2 or more, it became useState, then useReducer here. In React, actually errored out. So React is nice enough to keep track of this for us and refuse to run when it sees that happen. Nonetheless, we can see that it just doesn't make sense. And that error makes more sense to us because we understand how React works. Don't you think? Let's undo my bad changes and get back to our basic working application. We now see the rules of hooks. You can only call them from inside a function component, and they must be at the top level of your function. That is to say, they can't be inside anything that would call them a different number of times depending on some circumstance. Every call to your function component must be consistent in how it calls the hooks. Make sense? Let's move on. I hope you enjoyed the first 6 hours of my course, Understanding React, and I hope it helped you to understand React properly. If you'd like to keep going, head to understandingreact.com to sign up for the full course. And you can also follow the link in the description of the video. And even if you don't choose to get the full course, I hope this video was helpful to you in your coding and development journey. Thanks for watching. I'm Tony Alisea. Happy coding.